Now, the next point that we are going to discuss is u of t convolution of u of t is equal to r of t. So, u of t convolution of u of t is nothing but r of t. So, what's the meaning of this one? See, we can write u of t convolution of u of t is nothing but simply we can write integration from minus t u of term into t term. So, this is called as the integration because basically I've already told you f of t convolution of u of t is nothing but integration of the term is equal to minus to t f of term into d term. So this is basically the integration. So here replace f of t by u of t plus f of term by u of term. That's it. You are going to get this integration. This concept I already told you why it is like integration also. So f of t convolution of u of t is nothing but integration from term is equal to minus to t f of term into d term. So based on this concept only I have done. So integration of u of t is nothing but r of t. So that is the reason I have kept like this. Then e to the power of minus t into u of t, convolution of u of t is nothing but 1 minus e to the power of minus t into u of t. Basically I am going to give the general formula. So what is general formula? E to the power of minus 80 into u of t, convolution of e to the power of minus bt into u of t, 1 by b minus c into e to the power of minus 80 minus e to the power of minus bt into u of t. In place of b, substitute 0. Then what you are going to get in place of b, if you substitute 0, then you are going to get like this, which is equal to minus 1 by g into e to the power of minus 80, e to the power of minus 1 into u of t. So if you further simplify, what you are going to get 1 by a into 1 minus e to the power of minus 80 into u of t, right? So let me see what is the answer I have got here. 1 minus e to the power of minus t into u of t is equal to 1. They have substitute. If you substitute a is equal to 1, then you are going to get 1 into 1 minus e to the power of minus t into u of t. So I recommend you to remember this formula. If you remember this formula, in place of b substitute 0, in place of b substitute 1, then you are going to get this expression. Then cos t into u of t, convolution of u of t. See, I have already told you. This is f of t and this is u of t. So integration of f of t is nothing but integration of cos is nothing but sine derivative is cos. So sine derivative is cos and cos derivative is minus sine. So now the integration of cos is nothing but sine. Integration of sine is minus cos. Or in this case, the integration of cos is nothing but sine. Sine t into u of t. So therefore, I have already told you f of t convolution of u of t is equal to integration of the tau is equal to minus to t f of t b tau. So integration of cos is nothing but sin t. That's it, sin t into u of t. So now the next point is an LTI system having an impulse response h of t is equal to u of t is basically an integrator. I've already told you. Suppose if you take any LTI system with an impulse response h of t is equal to u of t, then by default the system is said to be an integrator because the output is the integration of the input. This is what same thing, right? F of t convolution of u of t and h of t is equal to u of t. So for any LTI system, if the impulse response is h of t is equal to u of t, then the different system is said to be integrated because the output is the integration of the input. So now the next point is impact of convolving any signal with u of t is the same impact of taking its integral. Same thing I have already told you. So impact of convolving any signal with u of t is the same as the impact of taking its integral. So as I have already told you, f of t convolution of u of t is equal to integration of the signal, which is integration of tau is equal to minus into t f of tau into d tau. So if you have any signal f of t, if you are going to convolve with u of t, then it indicates that it is basically integration of the signal f of t itself. So therefore we can say f of t convolution of u of t is equal to integration of tau is equal to minus into t f of tau into d tau. So basically whenever you are going to convolve f of t with u of t, it is simply we can say it is the integration of the f of t signal only. Integration of tau is equal to minus into t f of tau into d tau. So now the next point is f of minus t convolution of h of minus t is equal to y of minus t. As I have already told you, very simple point. Just as in this point I have already told you, f of t convolution of h of t is equal to y of t. I have already told you, suppose f of vat convolution of h of vat is equal to 1 by mod a into y of vat. So this one I have already told you. A can be either positive or a can be negative. Suppose a is equal to minus 1. in what I'm going to get f of minus t convolution of h of minus t is equal to 1 by mod of minus 1 is nothing but 1. So 1 into y of minus t. So therefore f of minus t convolution of h of minus t is equal to y of minus t. So by this formula, so I recommend to remember this formula. F of at convolution of h of at is equal to 1 by mod a into y of at. A can be either positive or A can be either negative. So this formula always you have to keep in mind. So f of t convolution of h of t is equal to y of t, then f of at convolution of h of at is equal to 1 by mod a into y of at. Then A can be either positive or A can be either negative also. This point always you have to keep in mind. So f of t convolution of h of t is equal to y of at, y of t. Then f of at convolution of h of at is equal to 1 by mod a into y of at. Then A can be either positive or A can be either negative also. This point always you have to keep in mind. So f of t convolution of h of t is equal to y of t. Then f of at convolution of h of at is equal to 1 by mod a into y of at. A can be either positive or A can be either negative. So in place of 3, if we substitute 1, in place of a, if we substitute minus 1, then I am going to get this one. So finally remember, f of t convolution of h of t is equal to y of t. And f of at convolution of h of at is equal to 1 by mod a into y of at. And A can be either positive or A can be either negative. In place of a, if we substitute minus 1, this relation I am going to get. So this is what I have written here. Then, I have already told you, convolution of even signal with even signal is equal to even signal. Convolution of odd signal and odd signal is equal to even signal. Convolution of even signal and odd signal is odd signal. And the convolution of odd signal and even signal is equal to odd signal. Same as the multiplication also. Same is going to satisfy by the multiplication also. So, even signal into even signal is equal to even signal. Odd signal into odd signal is equal to even signal. Even signal into odd signal is equal to odd signal. Odd signal into even signal is equal to odd signal. Same thing. Convolution and the multiplication both are same. We are going to have we have the same properties. Not the concept is the same. The properties are same. The properties are same. So therefore, we can say convolution or the multiplication of two even signals is even signal. Convolution or the multiplication of two odd signals is even signal. And convolution or the multiplication of even or odd or even is always equal to odd. So finally, I can say convolution or the multiplication of two even signals is always equal to even. Convolution or the multiplication of two odd signals is always even. And the convolution of either even signal or odd signal or odd signal or even signal is always odd. So this point always you have to keep in mind. The next point is, I've already told you, u of t convolution of u of t is nothing but r of t. Just now we have discussed. Because based on the concept f of the convolution of u of t is equal to integration of o is equal to minus into t f of dt. So based on this we can say r of t is equal to integration of the u of t, which is r of t is equal to integration of 2 is equal to minus into t u of dt. Then u of t minus t1 convolution of u of t minus t2 is equal to r of t minus of t1 plus t2. So this formula also I have already told you. What is the formula? Here listen carefully. Suppose f of t convolution of h of t is equal to y of t. Then f of t minus a convolution of h of t minus b is equal to y of t minus of a plus b. So this formula I already have told you. So f t minus a, f t minus b, here t minus of a plus b. Same concept here also they are applied. So u of t convolution of u of t is r of t. So here we have replaced t minus t1, we have t minus t2. So we have t minus of t1 plus t2. Based on this concept, so therefore get t minus t1, get t minus t2, get t minus of t1 plus t2. Based on the concept that we have discussed. Now the next formula is e to the power of minus t into u of t. Convolution of e to the power of minus t into u of t is equal to t into e to the power of minus t into u of t. Whereas e to the power of minus at into u of t, convolution of e to the power of minus bt into u of t is equal to 1 by b minus a into e to the power of minus at minus e to the power of minus bt into u of t. See, these both are different. These both are different. You may think that the substitute a is equal to 1 and b is equal to 1 and get this one. That is wrong. In this case, if you substitute a is equal to 1 and b is equal to 1, you will never get this case. If substitute a is equal to 1 and b is equal to 1, you will get 1 by 0, it is infinity. So these two are different. So you have to remember these two things. Even if you forget also, go for the Laplace domain. So the convolution of time domain will become product in the Laplace domain. So there you can go for Laplace domain and easily you can get the relation, the concept you can get, whatever the result you can get in a fraction of a second. But even if you remember this one, it's a very simple thing also. If you remember, it's a very easy also. So e to the power of minus t into u of t combination of e to the power of minus t into u of t is equal to t into e to the power of minus t into u of t. Similarly, e to the power of minus a to u of t combination of e to the power of minus b to u of t is equal to 1 by b minus a into e to the power of minus a t minus e to the power of minus b t into u of t. The next that we are going to discuss is about the commutative property. What's the meaning of commutative property? Suppose I have already told you commutative property. Suppose y is equal to f of t combination of h of t. Then you know the formula which is integration of y is equal to minus 70% into f of tau into h of t minus tau into d2. And this is a combination property, right? Integration of tau is equal to minus 70% into f of tau into h of t minus tau into d2. Similarly, y of t is equal to interchange these two things. H of t combination of f of t, which is equal to integration of y is equal to minus 70% into h of tau into f of t minus tau into d2. So, what's the meaning of commutative? Commutative means, suppose there is one system. Suppose there is one system. That is system. The input is f of t and the input response is h of t. Then the output y of t is equal to f of t combination of h of t. For the other system, the impulse response is f of t and the input is h of t. And the output is same as the previous case. That is the meaning of this one. So y of t is equal to f of t combination of h of t or y of t is equal to h of t combination of f of t. Still, in this both system, the response is same. So, for this system, the input is f of t and the input response is h of t. For this system, the input is h of t and the input response is f of t. So, in both these systems, the response is same. So, y of t is equal to f of t combination of h of t or y of t is equal to h of t combination of f of t. So, therefore, we can say that combination is going to satisfy the commutative property. So, y of t is equal to f of t combination of h of t, which is equal to integration of tau is equal to minus percent f of tau into h of t plus tau d2, or y of t is equal to h of t combination of f of t, which is equal to integration of tau is equal to minus percent h of tau into f of t plus tau into d2. So in both the cases, the result is same. So now the next point is any number of LTI systems in parallel can be combined into a single LTI system whose impulse response is sum of all the individual LTI system impulse response. Any number of LTI systems in parallel can be combined to a single LTI systems whose impulse response is a summation of all the individual LTI system impulse response. I have already told you. Suppose you take a pseudo number of LTI systems in parallel. So if you want a simplified version of the LTI system, then the simplified version LTI system impulse response is a summation of the individual system LTI systems impulse response. So therefore, you can say any number of LTI systems in parallel can be combined to a single LTI system whose impulse response is a summation of all the individual LTI system impulse response. So finally, I can say any number of LTI systems in parallel can be combined into a single LTI system and whose impulse response is a summation of all the individual LTI system impulse response. So in simple words, I can say, suppose you have so many number of LTI systems in parallel. And if you want to make a simplified version of this one, then the simplified version LTI system will have the impulse response, which is a summation of all the individual LTI systems impulse responses. And the next point is, any number of LTI systems started in cascade can be combined with a single LTI system whose impulse response is a combination of all the impulse response. Suppose if we have so many number of LTI systems in cascade, then the overall system will have the impulse response, which is a combination of each individual LTI system impulse response. So listen carefully, I can say like this. Suppose if you have so many cascade LTI systems, then the net LTI system, then the simplified LTI system impulse response is the combination of the individual LTI systems impulse responses. So any number of LTI systems that in cascade can be combined with a single LTI system whose impulse response is the combination of all the impulse responses. So if we have so many number of LTI systems in cascade, then the overall system LTI system impulse response is the combination of each individual LTI system. So now the next point is, a system is said to be linear if the equation is a linear differential equation. A linear differential equation is the one in which there are no product terms of input or output or derivatives and there are no constant terms. For example, a system is said to be linear if the equation is a linear differential equation. A linear differential equation is the one in which there are no product terms of input or output or derivatives, and there are no constant terms. So basically, suppose a given system is a linear system. So how to tell whether a given system is a linear system or not? By seeing its differential equation as a linear. Suppose for a given system, input and output there is some differential equation which is going to have some relation. There should be a linear differential equation. Then only we can say the given system is said to be linear. So how we can say a given differential equation is linear or not? If there are no product terms, of input and output or derivatives, and there are no constant terms. Constant term means +2, +3 like that. So if there are no constant terms and if there are no product of the inputs or the outputs or derivatives, then we can say the given differential equation is a linear differential equation. So finally, I can say, suppose if you have some system, and there is an input and output, there is some relation between them with the help of some differential equation. So if the differential equation is a linear, then only we can say the given system is said to be a linear system. So a differential equation is said to be a linear if there are no linear differential equation is one in which there are no product terms of input or no product terms of output or no derivatives or no product of derivatives, and there are no constant terms. Then we can say the given differential equation is said to be a linear differential equation. So the system is said to be linear. So in a given differential equation, if there are no product terms of input, or if there are no product terms of output, or if there are no product terms of derivative, then or there are no constant terms, then by default we can say it is a linear differential equation. So if there are no product terms of input or no product terms of output, or if there are no product terms of derivative, then and there are no constant terms, then we can say the given differential equation is said to be a linear differential equation. So finally, I can say that suppose if you have some system, so for a system there is an input and output, there is some relation between them with the help of differential equation. So how to say whether the given system is a linear or not? If the differential equation is a linear, then by default we can say it is a linear differential equation. Or we can say the given system is said to be a linear. So in the differential equation, there should not be no product terms of input, no product terms of output, or no product terms of derivative. And also there are no terms of constants like +2, +3 like that. Then we can say if all these conditions are satisfied, then we can say whatever is differential equation is a linear differential equation. So the system is said to be linear. So now the next point is, if all the coefficients occurring in a differential equation are independent of time, that is constants, then the differential equation is called as the constant coefficient differential equation, and the corresponding system defined by this differential equation is called as the time invariant system. So if all the coefficients occurring in a differential equation are independent of time, that is constants, then the differential equation is called as the constant coefficient differential equation, and the corresponding system defined by this differential equation is called as a time invariant system. Suppose if you have a system in that there is a input-output relation with the help of differential equation. Suppose if the constants are independent of time, or we can say they are constants. If the coefficients are the independent of time, or because they are constants, then we can say the given system is said to be a constant coefficient differential equation, and the given system is said to be a time invariant system. So we can say that. So we can say in simple words like that. So we can say in simple words we can say like this. Suppose if the differential equation is having a constant coefficients, then we can say it is a constant coefficient differential equation, and the given system we are going to call it as the time invariant system. So finally I can say like this. So for a given system, between the input and output there is a differential equation which is going to get real. And if the coefficients are constants, if the coefficients are constant, we can say it is a constant coefficient differential equation. Then we can say the given system is said to be a time invariant system. See, suppose if they are varying with, if the coefficients of a differential equation, if they are varying with time, means we can say it is a time variant system. If the coefficients of the differential equation they are constant, then we can say it is a time invariant system. So this point always you have to keep in your mind. So therefore simply we can say Suppose for a given system, if the differential equation coefficients are constant with respect to time, then it is called time invariant system. The coefficients are varying with respect to time, then it is called as a time varying system. So if all the coefficients occurring in a differential equation, if they are independent of time, that is constants, then the given differential equation is called as a constant coefficient differential equation, and the corresponding system defined by this differential equation is called as the time invariant system. So now the next point is, so an electrical system defined by differential equation is an LTI system only if the differential equation defined it is linear constant coefficient differential equation. Linear constant coefficient differential equation. So an electrical system which is defined by differential equation is an LTI system only if the differential equation is defined it is a linear constant coefficient differential equation. So what is the meaning of this one? So what is the meaning of LTI system in the format of differential coefficient? So this is the LTI system. So for the LTI system there is an input and there is an output. So there is some between the help of the differential equation there is some relation between the LTI system between the output and input. So that differential equation should be linear constant coefficient differential equation. So constant coefficient differential equation means we can say it is a time invariant system. Linear differential equation means we can say it is a linear. So it is going to have two properties, linear as well as time invariant. So therefore we can say it is a linear time invariant system. So whatever the detail for an LTI system is a gateway for an LTI system. The relation between input and output we are going to define with the help of differential equation. That must be a linear constant coefficient differential equation. Means there should not be any product terms of input, no product terms of output, no product terms of derivative, and also no constant terms. And also whatever the positions of the differential equation, it should be constant with respect to time. If all these are satisfied, then we can say the given system is a linear as well as a time invariant. So therefore finally we can say it is a linear time invariant system. So finally I can say for an LTI system, the input is x and output is y. So definitely there is some differential equation which is going to have some relation between the input and output. So definitely this differential equation should be always linear constant coefficient differential equation. Linear means there should not be no product terms of input, no product terms of output, or no product terms of derivative, and no constant terms. Then we can say it is a linear. And also whatever the coefficients of the differential equation, it must be constant. Then we can now the next point that we are going to discuss. Suppose this is the LTI system. So for this LTI system, the impulse response is h of n. Suppose if the input is e to the power of j omega naught n, then what is the output? E to the power of j omega naught into h of j omega naught, as I already told you. So therefore, e to the power of j omega naught n is called as the eigenfunction. Suppose for any LTI system of any impulse response h of n, if you are going to give e to the power of j omega naught as the input, then the output is the scalar multiple of that input. So that is the reason this is e to the power of j omega naught n is called as the eigenfunction for this LTI system. So listen carefully. For this LTI system of any impulse response h of n, if the input is e to the power of j omega naught n, then the output is the scalar multiple of that input, which is e to the power of j omega naught into h of j omega naught. So the output is the scalar multiple of the input. So that is the reason e to the power of j omega naught n is called as the eigenfunction for this system. Suppose if the input is e to the power of n, then what is the output y of n? I want to figure out. So y of n is nothing but simply we can say. So the basic formula. What is the basic formula? So the basic formula, which is y of n is equal to. So let me write here. So we can say y of n. So y of n is equal to x of n convolution of h of n, or you can write h of n convolution of x of n also you can write. So here x of n is equal to e to the power of n, and here h of n is as it is. So what is the formula here? Integration of it is summation k is equal to minus ∞2 plus ∞ h of k into x of n minus k. So now let me tell you, this is sigma k is equal to minus ∞2 plus ∞, h of k is as it is, and x the power of n, e to the power of n, and x the power of n minus k means wherever n is represented by n minus k, we are going to get e to the power of n minus k. As e to the power of n is a constant, we can take it outside this summation. So we are going to get e to the power of n into sigma k is equal to minus infinity plus infinity h of k into e to the power of minus k. So this is we are going to get here. So this is nothing but this is called as the h of a. So this is called as the is a function of a. It's a function of a. So therefore we can say a to the power of n into h of a. So it's a function of a. So we can write like this. So a to the power of n into h of a. So you can see clearly here same thing written. So y of n is equal to sigma k is equal to minus into plus into h of k into x of n minus k. So x of n is a to the power of n. So x of n minus k is e to the power of n minus k. As e to the power of n is a constant, we can take it outside summation. So e to the power of n into sigma k is equal to minus into plus into h of k into e to the power of minus k. So this value I can assume this is nothing but h of a. So e to the power of n into h of a. So we can say if e to the power of n is the input, then the output is e to the power of n into h of a. Suppose if k is the input, if k is the input means I assume a is equal to 1. If I assume a is equal to 1, then what I am going to get? Simply I can write. Suppose if a is equal to 1 means I can write like this. If it is 1 means I am going to get h of 1. Suppose we multiply k on both sides, then we are going to get k is nothing but k into h of 1. I can write like this. Suppose z to the power z0 over the power of n is inverse of a plus a over z0, then we are going to get z0 over the power of n into h of z0. Z0 is equal to r into e to the power of jn omega naught. So this is a general format we can say. So therefore we can say finally we can say that if a to the power of n is the input, then the output is a to the power of n into h of a. If k is the input, then the output is k into h of 1. If z0 over the power of n is the input, then output is z0 over the power of n into h of z0. Z0 is equal to r into e to the power of jn omega naught. So this is a general format. Suppose here if you are going to multiply by r, here also multiply by r, here also multiply by r. So this is nothing but so like this we can say generally this is the format that we are going to say. So this point always you have to keep in your mind. So I guess this is not n here, this is only j omega naught. So there is no n here. So there is no n here. So I can write like this as the z0 over the power of n. I can write z0 over the power of n. So what I can write here? Z0 over the power of n into h of z0. I can write. So here n is not there. It is r into e to the power of j omega naught. So here n is not there. So this point always you have to keep in your mind. So therefore we can say in simple words, if any output is the scalar multiple of input, then the gain input is called as the eigenfunction for the delta system. So in this case we can say e to the power of j omega naught n is called as the eigenfunction for this system. So finally I can say if the input is e to the power of j omega naught n, then the output is e to the power of j omega naught n into h of j omega naught. If a to the power of n is the input means the output is a to the power of n into h of a. If k is the input, the output is k into h of 1. If z0 over the power of n is the input, the output is z0 over the power of n into h of z0. If z0 is equal to r into e to the power of j omega naught. So this point always you have to keep in mind. So now the next point is for n-dimensional coordinate system there are n base vectors. So for n-dimensional coordinate system there are n base vectors. So this is a very simple point. Suppose if you take a n-dimensional coordinate system, then there will be n base vectors. See, for single dimensional coordinate system there is only one base vector. If you go for two-dimensional coordinate system there will be two base vectors. If you go for three-dimensional coordinate system there will be three base vectors. Means with the help of those three base vectors we can figure out any point on the three coordinate system. Similarly, for the one-dimensional coordinate system, with the help of one base vector, we can represent any point in the coordinate system. So simply I can say, for n-dimensional coordinate system, there will be n base vectors. So with the help of these n base vectors, we can represent any point in this n-dimensional coordinate system. So now the next point is, any signals can be defined based on base signals. Base signals similar to base vectors in linear algebra. So any signals can be defined based on the base signals. Base signals similar to the base vectors in linear algebra. So basically, I have already told you, in the linear algebra, with the help of base vectors, we can represent any point in the coordinate system. Similarly, with the help of base signals, we can represent any signal in the signal system course. So therefore, we can say, with the help of base vectors, we can represent any vector in the coordinate system. Similarly, with the help of base signals, we can represent any signal that we want. So any signal can be defined based on the base signals. So base signals are similar to base vectors in the linear algebra. So finally, I can say that base vectors, base vectors, with the help of base vectors, we can represent any vector. Similarly, with the help of base signals, we can represent any signal. So any signals can be defined based on the base signals. Base signals similar to base vectors in linear algebra. So finally, I can say with the help of base vectors, we can represent any vector in a dimensional system. Similarly, with the help of base signals, we can represent any signal that we really want. The next point is cos n omega naught t, sin n omega naught t. When n tends to 0 to infinity, then what is going to happen? See, cos n omega naught t and sin n omega naught t, these are called as the base signals. The value of n is varying from 0 to infinity. Suppose if you substitute n is equal to 0, then what you are going to get? Cos you are going to get 1, sin you are going to get 0. Suppose if you substitute 1, then you are going to get cos omega naught t, sin omega naught t. If you substitute 2, you are going to get cos 2 omega naught t, sin 2 omega naught t. So all the signals are called as the base signals. So with the help of these base signals, we can represent any signal that we want. So cos n omega naught t and sin n omega naught t, these are called as the base signals. The value of n is varying from 0 to infinity. So if you substitute n is equal to 0 to infinity, we are going to get 1 cos omega naught t, cos 2 omega naught t, and goes on. Similarly, here 0 sin omega naught t, sin 2 omega naught t, and goes on. So all these are called as the base signals. Each signal is orthogonal to the other signal in the time period t is equal to pi by omega period. So each signal is orthogonal to other signal in the time period t is equal to pi by omega period. So we can say all these signals are orthogonal to other signal. So each signal is orthogonal to other signal in the time period t is equal to pi by omega because omega is equal to pi by t. So t is equal to pi by t naught. So therefore we can say all these signals, one signal is orthogonal to the other signal. So one signal is orthogonal to the other signal in the time period t is equal to pi by omega because omega is equal to pi by t. So in this time period, each and every signal is orthogonal to the other signal in this domain. So these are called as the base signals. With the help of these signals, we can represent any signal that we want. So if you substitute n is equal to 0 to infinity in the cos of n omega naught t, we are going to get 1 to infinity. Similarly, the sin n omega naught t, substitute n is equal to 0 to infinity, we are going to get these things. So with the combination of all these signals, we can represent whatever signal that we want. So these are called as the base signals. So each signal is basically orthogonal to other signal in the time period t is equal to pi by omega naught period. The next point is e to the power of j n omega naught t. So e to the power of j n omega naught t. So this is also base signal. So this is also base signal, and the value of n is from -70%. So if this with the help of this concept, we are going to write the Fourier series, the trigonometric Fourier series, and with the help of this, we are going to write the exponential Fourier series. So with the help of this concept, we are going to write the trigonometric Fourier series, and with the help of this concept, we are going to write the exponential Fourier series. E to the power of j n omega naught t, and the value of n is lying from -m to +infinity. So if you substitute what you are going to get, which is from -m to infinity, you are going to get e to the power of -j omega naught t, and if you substitute n is equal to 0, we are going to get 1, and if you substitute 1, you are going to get e to the power of j omega naught t, and goes on. So n is lying from -m to +infinity. So you can substitute all these values of n. So you are going to get all this range. All these are called as the base signals. So each signal is orthogonal to other signal in the time period t is equal to pi by omega naught. So you know basically what's the time period? Omega naught is equal to pi by t. So t is equal to pi by omega naught. So whatever this each signal, it is basically orthogonal to other signal in the time period t is equal to pi by omega naught. So this point always you have to keep in your mind. So with the help of this concept, we are going to write the trigonometric Fourier series, and with the help of this concept, we are going to write the exponential Fourier series. So if you substitute n is equal to 0 to infinity, then we are going to get this range, and if you substitute n is equal to 0 to infinity in this one, we are going to get this range. All these are base signals. With the help of this, we are going to write the trigonometric Fourier series, and each signal is basically orthogonal to the other signal with time period t is equal to pi by omega naught. Similarly, e to the power of j n omega naught t, if the value of n is lying from -m to +infinity, if you substitute all the values of n from -m to +infinity, we are going to get all these things. So here also, each signal is orthogonal to other signal with time period t is equal to pi by omega naught. So with the help of this concept, we are going to write the trigonometric Fourier series, and with the help of this concept we are going to write the exponential Fourier series. So this point always you have to keep in your mind. The next point is here f of t is equal to, so basically what they have taken, these are the base signals, right? So these are the base signals. So these are the base signals. So with the help of the linear combination of these signals, we are going to get the new signal f of t that we require. So it's in the same fashion in the vectors also. With the help of linear combination of base vectors, we can get whatever the vector that we want. Similarly, with the linear combination of these base signals, we can get whatever the signal that we want. So f of t is equal to linear combination means multiply the constants a0 plus a0 into a1 into cos omega naught t plus a2 into cos omega naught t goes on plus here 0 must 0 as it is. Here it is basically b1 into sin omega naught t plus b2 into sin 2 omega naught t and goes on. So basically we have did the linear combination of these base signals in order to represent any signal that we want. So with the help of the linear combination of these signals, of these base signals, we can represent any signal that we want. So this is a linear combination of these base signals. So a0 plus a1 into cos omega naught t plus a2 into cos omega naught t and goes on plus 0 plus b1 into sin omega naught t plus b2 into sin omega naught t and goes on. So I can write this one in a simple fashion. F of t is equal to a0 plus sigma n is equal to 1 to infinity an cos omega naught t plus bn sin omega naught t. So this one I have represented in the same fashion. If substitute n is equal to 1 to infinity, we are going to get this series in this one. Similarly, if substitute n is equal to 1 to infinity in this term, then we are going to get this series. And a0 is a constant. So this is called as a trigonometric Fourier series or the real Fourier series. So this is also called the trigonometric Fourier series or the real Fourier series. So this one always you have to keep in your mind. So all signals have a common time period which is 2 pi by omega naught. So if you see this first signal has a time period which is 2 pi by omega naught. This signal is also have a time period of 2 pi by omega naught. This signal is also have a time period of 2 pi by omega naught. And this signal is also have a time period of 2 pi by omega naught. So all the signals will have the same time period. So for all the signals, if you are going to add the constant a0, still the signal is a periodic signal. So for any periodic signal, if you add a constant, then still the overall signal is also a periodic signal. So still the period is same, which is nothing but 2 pi by omega naught. So all the signals have a common time period which is nothing but 2 pi by omega naught. So f of t is also a periodic signal which has a time period of 2 pi by omega naught. So therefore we can say all these signals have a common time period which is 2 pi by omega naught. So even though you are going to add with constants, so the time period is same. So f of t is also a periodic signal which has a period of 2 pi by omega naught. So f of t is also a periodic signal with a time period 2 pi by omega naught. If f of t is a random signal, then this equation holds only up to 0 less than or equal to t less than or equal to 2 pi by omega naught. Suppose if you are taking f of t is a random signal, then this equation is going to hold only for the t lies from 0 to 2 pi by omega naught. So basically, suppose if f of t is a periodic signal, then this equation is going to hold for all time with a time period 2 pi by omega naught. Suppose if f of t is a periodic signal, then this equation is going to hold for all the value of time. Suppose if f of t is a non-periodic signal, a random signal, then the equation is going to hold only for this range of time. So simply we can say, suppose if f of t is a random signal or non-periodic signal, then this equation is going to only for time period of 0 to 2 pi by omega naught. Suppose if f of t is a periodic signal, then this equation is going to hold for all the values of time t, which has a period of 2 pi by omega naught. So finally, I can say, suppose if f of t is a random signal, then this equation is going to hold only for a time of 0 to 2 pi by omega naught. Suppose if f of t is a periodic signal, then this equation is going to hold for all the value of t, and this f of t is a time period of 2 pi by omega naught. So now we will do some analysis. So this analysis already I have told you, but again let me tell you. So this analysis I am going to further do the analysis of this part. A into cos n omega naught t plus b into sin omega naught t, I am going to do the analysis. So this one I am going to write in the fashion of r into cos of n omega naught t minus phi n. I have already told you how to write this one. So cos a cos b plus sin a sin b is equal to cos of a minus b. So you know cos a minus b is equal to cos a cos b plus sin a sin b. So you know cos a is equal to an cos a cos b plus sin a sin b. So from this I have already told you how to prove this one. I have already told you. So r we are going to it's under root of n square plus b n square, and phi n we are going to get tan inverse of Bn by An. Already I have proved. How I proved here? So let me take here cos A minus B is nothing but cos A minus B is nothing but cos A cos B plus sin A sin B means cos n omega naught t into cos phi n plus sin phi n into sin n omega naught b. So we can say cos phi n is equal to En, sin phi n is equal to Bn. So take this squaring on both sides, then we are going to get, which is nothing but simply we are going to get like this. So what we are going to get? Very simple. As I already told you, let me write here. So let me write here again so that we can easily able to understand what I am trying to tell you. So here we can see clearly that cos, see, I already told you it is Rn into cos phi n into cos n omega naught t plus sin phi n into sin n omega naught t. So take Rn inside, and what we are going to get? We will take Rn inside, we are going to get Rn into cos phi n omega naught t plus Rn into plus Rn into sin phi n into sin n omega naught t, which is equal to, simply we can say An cos n omega naught t plus Bn sin n omega naught t. So by comparing, what we can say? Rn into cos phi n is equal to An. Rn into sin phi n is equal to Bn. So by the squaring on both sides, then we are going to get Rn is equal to An square plus Bn square. So by the squaring on both sides and by the summation, we are going to get finally Rn is equal to An square plus B square. And divide the equation 2 by equation 1, then we are going to get phi n is equal to tan inverse of Bn by An. So this is what I already proved here. So let me write here. So therefore Rn is nothing but under root of An square plus Bn square, and phi n is nothing but tan inverse of Bn by An. So what I can write here? So this I can simplify it like this, which is Rn into cos n omega naught t minus phi n I can write. So f of t is equal to naught plus sigma n is equal to 1 to infinity Rn into cos of n omega naught t minus phi n. So what I will do now, here, instead of this I will go for sigma n is equal to 0. Instead of n is equal to 1 to infinity, I will go for sigma n is equal to 0 to infinity Rn into cos n omega naught t minus phi n. So I will substitute n is equal to 0, then what I am going to get? Then R0 into cos of this is 0. So cos of minus phi n is nothing but cos phi naught. So what we are going to get if we substitute n is equal to 0, we are going to get R naught into cos of phi naught we are going to get. So you know Rn is nothing but under root of A square plus Bn square. So R naught means under root of A naught square plus B naught square. As B naught is equal to 0, so as B naught is equal to 0, so R naught we are going to get A naught. Then as B naught is equal to 0, then definitely what is phi naught? Phi naught is equal to inverse of B naught by A naught. As B naught is equal to 0, so phi naught is also equal to 0. So therefore R naught is equal to A naught and phi naught is equal to 0. Because B naught is equal to 0, I already told you. So B naught is equal to 0 in this case. So therefore we can say finally f of t we can write, which is equal to sigma n is equal to 0 to infinity Rn into cos n omega naught t minus phi n, where R naught is equal to A naught and phi naught is equal to 0, because cos 0 is equal to 1. So you are going to get only A naught, you are going to get the constant if substitution is equal to 0 and B naught is equal to 0. So omega naught is called as a fundamental or the first harmonic frequency. Suppose if we substitute n is equal to 1, then what we are going to get? First harmonic frequency or the fundamental frequency. And if you substitute n is equal to 2, then we are going to get the second harmonic. If you substitute n is equal to 3, we are going to get third harmonic. If you substitute n, we are going to get nth harmonic frequency. So therefore, if you substitute n is equal to 1, which is called as the first harmonic frequency or the fundamental frequency. If you substitute n is equal to 2, which is called as the second harmonic or the second harmonic frequency. And if you substitute n is equal to 3, then we say it is a third harmonic frequency. And if you substitute n is equal to 4, we say it is a fourth harmonic frequency. Similarly, if you substitute at n, then we are going to get nth harmonic frequency. So n is equal to 1 means we are going to get the fundamental frequency or the first harmonic frequency. So if you substitute n is equal to 1, then we are going to get the fundamental or the first harmonic frequency. So if you substitute n is equal to 1, then that is called as the first harmonic or the fundamental frequency. If you substitute n is equal to 2, which is called as second harmonic frequency. If you substitute n is equal to 3, which is called as a third harmonic frequency. So generally, if you substitute n is called as the nth harmonic frequency. So these things always you have to keep in your mind. And this is called as the amplitude phase form. So this is the amplitude phase forms is called as the amplitude phase form. And this is called the trigonometric Fourier series or the real Fourier series. and this is called as the amplitude phase form. Amplitude phase form. These are the different ways always you have to keep in mind here. The next point is, suppose f of t is equal to sigma n is equal to minus m to plus m t cn into the power of j n omega naught t. So this is called as the exponential form of the Fourier series or the complex Fourier series. So this is called as the exponential form of the Fourier series representation or the complex Fourier series representation. So here all terms in this expression has a time period 2 pi by omega naught. So if you see clearly, so from this only, so these are the basic signals, right? So from this basic signal only, we have got this one. How? They are multiplied 1 with C naught. For this one, multiply by C1, C2 and goes on. Here minus C1, minus C2, C minus 2, C minus 3 and goes on. So you are going to get this thing. And in the terms, you are going to get this term and this term. So if you add all these things, we are going to get the sigma formula, which is sigma and is equal to minus 70 plus 70 Cn into e to the power of j n omega naught t. So these are the basic signals. The linear combination of these signals, then we are going to get this one. So with the help of this linear combination, we can represent any periodic signal that we want. So this is the exponential form of the Fourier series, or it is also called as a complex Fourier series. So these points always you have to keep in your mind. So therefore, this is called as exponential form of the Fourier series or the complex Fourier series. So all terms in this expression has a time period 2 pi by omega naught. So if you see, e to the power of j omega naught t is a time period 2 pi by omega naught. E to the power of j2 omega naught t is also time period 2 pi by omega naught. And similarly, this is the basic time period. The actual time period is somewhat lesser, but they have a common time period of 2 pi by omega naught. So this also has a time period of 2 pi by omega naught. So if you add one means simply we can say, if you add one means definitely it is again a periodic signal. So means here if substitute n is equal to 0, we are going to get C naught. So C naught plus all those signals. So if you do the linear combination of all these things, again it is a periodic signal. So f of t is also a periodic signal with a time period of 2 pi by omega naught. So all terms in this expression has a time period of 2 pi by omega naught. So therefore f of t also time period just is equal to 2 pi by omega naught. So this is called as the trigonometric Fourier series or the real Fourier series, and this is called as the exponential Fourier series or the complex Fourier series. So now the next point is Fourier series valid from minus m to plus m t when f of t is a periodic. Fourier series valid from 0 to 2 pi by omega naught when f of t is a random signal. I already told you. See, whatever this expression is valid for a periodic signal from minus m to plus m t, supposable if it is a random signal, then this expression is going to valid only for 0 to 2 pi by omega naught. So finally I can say, suppose if a given signal f of t is a periodic signal, then this Fourier series expression is valid from t is equal to minus m to plus m t. Suppose if f of t is a random signal or a periodic signal or any signal, then this Fourier series expression is valid from only 0 to 2 pi by omega naught. So finally I can say, suppose if f of t is a periodic signal, then this Fourier series expression is valid from t is equal to minus m to plus m to t for all values of t. Suppose if f of t is a random signal, then this Fourier series expression is going to be valid only from 0 to 2 pi by omega naught. So this point you have to keep in your mind. So let me write this trigonometric Fourier series or the real Fourier series, which is f of t is equal to e naught plus sigma n is equal to 1 to infinity again cos n omega naught t plus bn sin n omega naught t. So what are the Fourier series coefficients a naught, an, bn? So what are these values? Which is a naught is equal to 1 by t integration over the one time period f of t into dt. An is equal to 2 by t integration over the one time period f of t into cos n omega naught t dt. And bn is equal to 2 by t integration over the one time period f of t into sin n omega naught t dt. So where a naught is called as the DC value or the average value. So the a naught is called as the DC value or it is also called as the average value. Why? Because the average value of this cos n omega naught t is equal to 0 average value, and its average is also equal to 0. So the only thing which is going to present is a naught. So f of t average is nothing but simply we can say a naught. So that is the result. A naught is called as the average value or the DC value because the average value of the cos n omega naught is always equal to 0 and the average value of the sin n omega naught is nothing but 0. So only a naught here going to be present. So f of t average is equal to a naught. So that is the reason a naught is also called as the DC value or the average value. So a naught is equal to 1 by t integration over the one time period f of t dt. An is equal to 2 by t integration over the one time period f of t into cos n omega naught t dt. And bn is equal to 2 by t integration over the one time period f of t sin n omega naught t dt, where a naught is called as the DC value or the average value. So now let's go for the exponential Fourier series. F of t is equal to sigma n is equal to minus n to plus infinity Cn into e to the power of jn omega naught t. So this is a complex, you can say complex Fourier series or the exponential form of the Fourier series. So for this one, there is only one Fourier series called it is Cn. Cn is equal to 1 by t introduction of the one time period f of t into here plus means write it here minus e to the power of minus jn omega naught t dt. That's it. Here plus means here right, take it minus. That's it. So Cn is equal to 1 by t introduction of the minus t by 2 to t by 2 f of t into e to the power of minus jn omega naught t dt. Suppose if you substitute n is equal to 0, then what you are going to get? If you substitute n is equal to 0, this value we are going to get 1. So the remaining thing is nothing but 1 by t introduction of 1 time period f of dt is nothing but a naught. So that is the reason C naught is equal to a naught. And what is Cn? Cn is nothing but, just expand. You know, e to the power of j theta is nothing but cos theta plus j sin theta. The theta is equal to minus n omega naught t. And if you substitute and if you expand, and if you try to expand, finally you are going to get in this fashion. 1 by t introduced to the one time period f of t into cos n omega naught t dt minus j into 1 by t introduced to the one time period f of t into sin omega naught t dt. So this is nothing but an by 2 and this is nothing but bn by 2. So an by 2 minus j bn by 2. So Cn is nothing but an by 2 minus j bn by 2. Because if we expand this one, we are going to get this is nothing but an by 2 and this is bn by 2. So Cn is equal to n by 2 minus j bn by 2. Suppose in place of n, if I substitute minus n, then what I am going to get? C of minus n is equal to 1 by t introduced to the time period f of t. E to the power of in place of n, I substitute minus n, so you are going to get plus j n omega naught t dt. Again, if you expand, then what you are going to get? With the plus n, you are going to get here plus n. So this is a n by 2 plus j bn by 2. So n by 2 plus j bn by 2. So from this we can say one is the conjugate of the another. So C of n is the C conjugate of C minus n conjugate. Or you can take reverse also. Cn conjugate is nothing but C of minus n. Where n is a value from 1 to and so on. So therefore we can say C naught is equal to 0. So C naught is equal to a naught and Cn is equal to an by 2 minus j bn by 2 and C of minus n is nothing but an by 2 plus j bn by 2. So we can say one is the complex conjugate of the other. So Cn is Cn minus n conjugate. Similarly, C minus n is equal to Cn conjugate. So we can say one is the conjugate of the another thing. So n value is varying from 1 to infinity. So n value is nothing but is varying from 1 to infinity. So from this, if you substitute here 1 to infinity, we are going to get C1, C2, C3. If you substitute here n is equal to 1 to infinity, we are going to get C of minus 1, C of minus 2 and goes on. So here if you substitute n is equal to 1, 2 and goes on, means we get C1, C2, C3 like that. Here if you substitute n is equal to 1, 2 and goes on, means C minus 1, C minus 2, C minus 3 like that we are going to get. So here when f of t is the real value signal. So these are the things always you have to keep in your mind. So when f of t is the real value signal. So Cn is the even conjugate. So Cn is called as the even conjugate signal. Because you can see Cn is the an by 2 minus j bn by 2. So you see the real part is even nature. So that is the reason it is called as the even conjugate, because the real part, if you see clearly, what I can say, see, if you see clearly, here the real part is same, but the imaginary part is, it is odd nature. So you can say the real part is even nature and the imaginary part is odd nature. So for Cn is nothing but the real part is even nature and the imaginary part is odd nature. One is plus means the other is minus. So Cn is nothing but even conjugate, because you can say even conjugate means the real part is even and the imaginary part is odd in nature. And you know what is Rn? Rn, you know, I've already told you Rn is equal to root over n square plus bn square. And you know, phi n is nothing but tan inverse of bn by an. So minus phi n means multiply minus on both sides, we are going to get minus phi n is equal to minus tan inverse of bn by an. So now, what you are going to get? See, I've already told you. Suppose if you simplify, what you are going to get here? If you simplify, you are going to get. So we can write like this, right? Under root over an by 2 whole square plus bn by 2 whole square means what you are going to get? Simply under root over an square plus bn square by 2, it is nothing but Rn by 2 you are going to get. Here, minus of tan inverse of bn by an is minus phi n you are going to get. Here you are going to get Rn by 2 plus phi n you are going to get. Solution I have already told you. So If you, this is a rectangular format, so try to convert the polar format, we are going to get Rn by 2 into phase angle of minus phi n. And this one we are going to get Rn by 2 at a phase angle of phase plus phi n. So Rn is nothing but root over n square plus b n square, and plus phi n is tan inverse of bn by n, minus phi n is nothing but minus tan inverse of bn by an. So now it is a magnitude spectrum because n value is discrete nature. N value is a discrete nature. So I will take only the values of n omega naught. With respect to n omega naught, I am going to draw the vector, to draw the waveform. So Rn, you know, Rn is nothing but root over n square plus bn square. So if you see clearly, see this is the Rn, right? So this is the Rn. So if you substitute n omega naught, means n is equal to 0, then what you are going to get? R naught you are going to get. If you substitute n is equal to 1, then we are going to get R1 we are going to get. If you substitute n is equal to 2, we are going to get R2. Like that we are going to get here. So this is called the magnitude spectrum. This is called the magnitude spectrum. And this is called the phase spectrum. So phase spectrum is nothing but minus phi n. So if you substitute here with the n is equal to 1, then we are going to get what we are going to get? Minus phi 1, minus phi 2, minus phi 3. Like that we are going to get. So this is the magnitude spectrum and this is the phase spectrum. Because the n value is discrete in nature. So magnitude spectrum is discrete in nature and the phase spectrum is also discrete in nature. The magnitude spectrum is always an even function and the phase spectrum is always an odd function. As you can see, for Cn and C of minus n, the magnitude is same, only the phase angles are opposite in nature. So we can see the magnitude spectrum is real spectrum, means even spectrum, and the phase angle spectrum is an odd spectrum, as you can see clearly from this picture. So magnitude spectrum is a real spectrum, magnitude spectrum is an even spectrum, and the phase spectrum is an odd spectrum, as you can see clearly from this picture. So these things always you have to keep in your mind here. We are going to discuss the another point, which is h of j omega naught is equal to integration of tau is equal to minus m to plus m t h of tau into e to the power of minus j omega naught tau d tau. So this is called as the Fourier transform of the h of t. As I've already told you, what is the Fourier transform for any signal f of t? I've already told you for a signal f of t, what is the Fourier transform expression? I've already told you which is f of omega is equal to integration of tau is equal to minus infinity to plus infinity f of t into e to the power of minus j omega t into dt. So this is basically t, not tau. So t is equal to minus infinity plus infinity f of t into e to the power of minus j omega t into dt. So now suppose for h of t, so for h of t, what is our Fourier transform? H of omega or h of j omega, which is same. Integration of t is equal to minus infinity to plus infinity h of t into e to the power of minus j omega t dt. Here either you can use t as a dummy variable or tau as the dummy variable. You can use anything. For influence of omega, if it is omega naught plus, you have to write here also omega naught. Same thing here. Influence of t, I have written tau, and here omega is nothing but omega naught. So this is called as the Fourier transform of the h of t. The h of t is the impulse response for an API system. So the next point is trigonometric Fourier series has three integrals in order to figure out the Fourier coefficients. I have already told you, in the case of the trigonometric Fourier series, we have three integrals in order to figure out the Fourier series coefficients. So what are those three integrals? Just now we have discussed a0, an, and bn. So if you want to write the trigonometric Fourier series expression, then you know the value of a0, you know the value of an, and also you need to know the value of bn. So these three integrals we have to calculate. Then only we can write the trigonometric Fourier series expression. So trigonometric Fourier series has three integrals in order to figure out the Fourier series coefficients, whereas the exponential Fourier series has only one integral in order to figure out the Fourier coefficients. So whereas the exponential Fourier series has only one integral in order to figure out the Fourier series coefficient. So you can see, whereas in the exponential Fourier series, if you want the Fourier series coefficient, you need to do only one integral. Whereas here you have to do three integrals, and here you have to do only one integral. So whereas in the exponential Fourier series, we have only one integral in order to figure out the Fourier series coefficient. So whereas in the trigonometric Fourier series, you have to do three times the integral in order to figure out the Fourier series coefficients. Whereas in the exponential Fourier series, you have to do only one integral in order to figure out the Fourier series coefficient. So same thing everything here. trigonometric Fourier series has three integrals in order to find the Fourier series coefficients, which are A0, an, and Bn. Whereas the exponential Fourier series has only one integral in order to find the Fourier series coefficient, which is Cn. In exponential Fourier series, complex macro spectrum is even spectrum symmetry, whereas a complex phase spectrum is all spectrum symmetry. I've already told you, in the case of the exponential Fourier series, Cn we are going to get. Cn is nothing but, it's a complex number. So Cn is nothing but an minus jb, an by 2 minus jn bn by 2. So this is a rectangular format. So if you write in a polar format, we are going to get like this. So if you see clearly, that this magnitude is an even spectrum and this phase spectrum is an odd spectrum. So therefore, in exponential Fourier series, the complex magnitude spectrum is even spectrum symmetry, whereas the complex phase spectrum is an odd spectrum symmetry. Means in the case of the exponential Fourier series, Cn is nothing but n by 2 minus jbn by 2. So this is a complex number. So if you write in the rectangular format, so if you write in the polar format, we are going to get Rn by 2 of the phase angle of minus 5n. So this is an even spectrum. The magnitude spectrum is an even spectrum, and the phase angle spectrum is an odd spectrum. So therefore, we can say in exponential Fourier series, the complex magnitude spectrum is an even spectrum symmetry, whereas the complex phase spectrum is an odd spectrum symmetry. The next thing is, because of computational easy, exponential Fourier series is easy to use. So because of the computational easy, exponential Fourier series is easy to use. So basically, if you want to know which one is easier, if you see here, we want to do 3 times the integral in order to figure the value of Bn. But here we have to use only one integral in order to figure the value of Cn. So from this we can say, this is simple because the competition is less. This is harder because the competition is very high. So therefore we can say, if you want to see the terms of the computation, here for this one the competition is very less, but for this one the competition is very higher. So you can see for the exponential part the amount of simple competition is very less, whereas for the trigonometry the competition is very higher. So that is what I am trying to tell you. So because of the computational easiness, exponential Fourier series is always easy to use. The next thing is, complex Fourier series is only a medium in order to get a real Fourier series called as the trigonometric Fourier series. That is, there is nothing like complex spectrum occurring in reality. It is only a medium to realize the real spectrum in simple case. Hence, we all to derive complex spectrum due to computational simplicity, we must always look at real spectrum with the following observations. So complex Fourier series is only a medium in order to get a real Fourier series, which is called as a trigonometric Fourier series. Means I already told you, just by knowing the complex Fourier series, with the help of that we can even get the trigonometric Fourier series. I already told you. If you know Cn, then you can get the value of An, you can get the value of Bn, just by coming the real part and imaginary part. And C0 is equal to A0. From that we are going to get the value of A0. So if you know the complex, Fourier series, then we can easily get the trigonometric Fourier series also by comparing the coefficients. So therefore you can say complex Fourier series is only a medium in order to get a real Fourier series, which is called as a trigonometric Fourier series. So you always try to figure out the exponential Fourier series for a single f of t. Then by using this comparison method, by coming the real part and imaginary part, we can get the value of A0, An and Bn. So from that we can get the real Fourier series or the trigonometric Fourier series. So there is nothing like complex spectrum occurring in reality. So there is nothing like complex spectrum is occurring in reality. It is only a medium to realize the real spectrum in simple case. So basically we are doing this complex spectrum in order to make things very simple. So from this we can get the trigonometric series in a very easy manner. Hence we have to derive complex spectrum due to computational simplicity. We must always look at the real spectrum with the following observations. So therefore, what I am trying to do is very simple. So basically, for any signal periodic scale f of t, always we try to figure out the exponential Fourier series. Because it is a very easy because of less computation in order to get the value of Cn. So if you know the Cn, then you can get the value of An and Bn by coming the real part and imaginary part. And C0 is nothing but A0. So if you know the exponential Fourier series, then you can easily get the trigonometric Fourier series for the signal f of t. So in the case of computational easiness, first we will try to figure out the exponential Fourier series, and then with the help of the observations, By comparing, we can get the real Fourier series or the trigonometric Fourier series. See, in reality, there is nothing like complex matrix spectrum or complex phase spectrum, but there is only real phase spectrum and the real matrix spectrum that we can easily get from the exponential Fourier series. Therefore, complex Fourier series is only a medium in order to get a real Fourier series, which is called as the trigonometric Fourier series. That is, there is nothing like complex spectrum occurring in reality. It is only a medium in order to realize the real spectrum in a simple case. Hence, you have to derive complex spectrum due to computational simplicity. We must always look at the real spectrum with the following observations. So finally, I can say complex Fourier series is only a medium in order to get a real Fourier series, which is called as the trigonometric Fourier series. That is, there is nothing like complex spectrum occurring in reality. It is only a medium in order to realize the real spectrum in simple case. Hence, we are to derive complex spectrum due to computational simplicity. We must always look at the real spectrum with the following observations. So in simple words, I can say like this, which is basically here, I've already told because of the computational easiness, we try to figure out the exponential Fourier series. Then, with the help of comparing the real part and imaginary part, we try to figure out the real Fourier series or the trigonometric Fourier series. And also, I've already told that there is something like complex spectrum in reality. But with the help of this exponential Fourier series, we are going to get the Fourier and the real Fourier series or the trigonometric Fourier series. So this is only a medium. This exponential is a very medium, only a medium, a simple analysis in order to get the real spectrum and the real Fourier series. So this is the point I am trying to tell you. The next thing is to address a frequency occurring in the complex spectrum, consider only the physically possible positive frequencies. So if you see in the exponential Fourier series, when you draw the matter spectrum and phase spectrum, here you have the positive frequency and the negative frequency. But in reality, there is nothing like negative frequency. So always see only the positive frequency, only see only the positive frequency, only see. There is nothing like negative frequencies in the real world. There are only positive frequencies. So always see your observation only in the positive frequency only. See your observation. So you have to see only the positive frequencies spectrum, matter spectrum and the phase spectrum. Only the positive frequencies you have to see, but not in this manner, not in this way. So not in this negative frequencies. In order to address the frequency occurring in complex spectrum, consider only the physical possible positive frequencies. To address the frequency actually occurring in the complex spectrum, consider only the physically possible positive frequencies. See the case of exponential Fourier series. In the matter spectrum and phase spectrum, they are the positive frequencies and negative frequencies. So don't see the negative frequencies, only see the analysis of the matter spectrum and phase spectrum with the positive frequency only we have to see. Only you have to see only this one, only these things you have to see, but not this one, because there is nothing like negative frequencies in the real world. Only positive frequencies are there in the real world. So you have to see only these things. So this point always you have to keep in your mind. Now, the next point is, in evaluating the energy and the power, which are both magnitude-based applications. So looking at the complex magnitude spectrum, consider the magnitudes occurring for both the positive as well as the negative. So in evaluating the energy and the power, which are both the magnitude-based applications, so looking at the complex magnitude spectrum, consider the magnitudes occurring for both the positive as well as the negative frequencies. For both the positive and the negative frequencies, here are the positive and the negative frequencies. So basically, what I am trying to tell you, suppose basically whenever you want to evaluate the energy as well as the power of a signal, which are basically which both of these concepts are the magnitude-based applications. So therefore, if you are going to look at the complex magnitude spectrum, then consider the magnitudes occurring for both the positive as well as the negative frequencies. So I have already told you, if you want to evaluate the energy and if you want to evaluate the power of a given signal f of t, which are basically the magnitude-based applications. So therefore, you have to consider the magnitudes in the positive frequency as well as the negative frequency in the magnitude spectrum. So in simple words, I can say, suppose for a given signal f of t, if you want to calculate the energy as well as the power, which are basically the magnitude-based applications. So therefore, you have to consider the magnitudes in the positive frequency as well as the negative frequency in the magnitude spectrum in the magnitude spectrum. So this point always you have to keep in your mind. So therefore we can say, if you want to, so when you are going to evaluate the energy as well as the power of a given signal f of t. So when you are going to evaluate the energy as well as the power of a given signal f of t, which are basically the magnitude based, which are the magnitude based applications. So therefore, you have to consider the magnitudes in the positive frequencies as well as the negative frequencies of the given signal while calculating the energy as well as the power. So finally, I can say, if you want to calculate the energy and the power of a given signal f of t, which are basically the magnitude based concept, so you have to consider the magnitudes in the positive frequencies as well as the negative frequencies in the magnitude spectrum of a given signal. So therefore, in evaluating the energy and the power, which are both the magnitude based applications, so looking at the complex magnitude spectrum, consider the magnitudes which are occurring for both the positive frequencies as well as the negative frequencies. The next point is, to address the real phase information, looking at complex phase spectrum, address the phase information occurring for only the positive frequencies. To address the real phase information looking at the complex phase spectrum, address the phase information occurring only for the positive frequencies. Suppose what I am trying to tell you, in the trigonometric Fourier series and in the exponential Fourier series, so positive frequencies means only the positive frequencies are going to occur in real world. So whatever the phases which are occurring for the positive frequencies, those phases only you have to include in the trigonometric Fourier series. So whatever the phases which are occurring in the positive frequencies, only these phases we have to use while writing the trigonometric Fourier series. So therefore we can say that in simple words I can say like this. In simple words I can say like this. So what is the simple words I can say? Which is in simple words I can say like this, which is basically that. So in the simple words I can say like this, which is basically that the whatever the phases which are occurring at the positive frequencies, only these phases you have to utilize. Those phases you have to utilize while writing the trigonometric Fourier series. So in order to address the real phase information looking at the complex phase spectrum, address the phase information occurring only for the positive frequencies. So in simple words I can say, suppose whenever you are going to see the phase spectrum, instead it is obtained from the complex Fourier series expression. So you have to see only the phase spectrum of the positive frequencies. From that we can derive what is the phases in the trigonometric Fourier series. So therefore see only for the positive frequencies, see the phase, and you have to include this one in the trigonometric Fourier series expression. Negative frequencies are not possible but are used for only for simplifications. So negative frequencies are not possible but are used only for simplification. So in the real world there is nothing like negative frequencies. So in the real world there is nothing like negative frequencies, but we are going to use them only for the simplification. So we are going to use them only for the simplification purpose only. So in the real world there is nothing like negative frequencies. So we are going to use them only for the simplification purpose only. So in the real world there is something like negative frequencies. We are going to use the negative frequencies only for simplification purpose only. So this point you have to keep in your mind. So now the next point is, suppose if f of t is a real and even signal. I have already told you what is the meaning of this one. Suppose if f of t is the real and even, and what is going to happen? So f of t is the real as well as the even signal. So then f of t is equal to f of minus t. And normally we can basically say to be the even signal. It is an even signal. And what is going to happen? See, I already told you, suppose when the signal is even signal, then a0 is not equal to 0, an is not equal to 0, but bn is equal to 0. I already told you. So from this we know c0 is equal to a0, cn is equal to an by 2 minus j bn by 2. See, as a0 is not equal to 0, so c0 is also not equal to 0. As an is not equal to 0, but bn is equal to 0, so cn is nothing but real. Cn is only really real. So therefore we can say when f of t is a real and even signal, then c of n is nothing but purely real. So therefore a0 is not equal to 0, an is not equal to 0, and bn is equal to 0. So therefore we can say simply, if f of t is a real as well as the even signal, then I already told you even signal means f of t is equal to f of minus t. So therefore a0 is not equal to 0, an is not equal to 0, and bn is equal to 0, and c0 is equal to a0, and cn is equal to n by 2 minus j bn by 2. So from this we can say Cn is not purely real in nature. Suppose if f of t is the odd signal, then what is going to happen? If f2 of t is the real as well as the odd signal, then what is going to happen? This f of t is equal to f of minus t is equal to minus of f of t. So f of minus t here, right here. So f of minus t is equal to minus of f of t. Then we say the signal is said to be odd signal. So in that case, what is going to happen? A0 is equal to 0, An is equal to 0, and Bn is not equal to 0 in that case. So what is C0? C0 is equal to A0, Cn is equal to An by 2 minus j Bn by 2. So as An is equal to 0, so Cn is purely imaginary. It is purely imaginary. So therefore we can say that when the f of t is a real as well as odd signal, then A0 is equal to 0, An is equal to 0, and Bn is not equal to 0. So therefore, C0 is equal to A0, Cn is equal to N by 2, and J Bn by 2. If we substitute these values, we can say A0 is also, and C0 is also equal to 0. So C0 is also equal to 0, and Cn is purely imaginary. It is purely imaginary because N is 0. So same thing we have written. So therefore, we can say when f of t is a real and odd signal, then Cn is purely imaginary. Suppose if f of t is a general signal which is a real, means it is neither a real signal, neither an odd signal. Then what is going to happen? Then A0 is not equal to 0, An is not equal to 0, and Bn is not equal to 0. So definitely then Cn is nothing but complex nature. And I've already told you, the real part of Cn is always even in nature, and the imaginary part of Cn is always odd nature. This one I've already told you so many number of times. The real part of Cn is always even nature, and the imaginary part of Cn is always odd nature. This point I've already told you. So therefore, we can say when f of t is a real as well as an even signal, then we can say Cn is purely real. If f of t is a real and odd signal, then Cn is purely imaginary. Suppose if f of t is a general as signal and it is a real, then this is neither a real, it is neither even signal, it is neither an odd signal, then Cn is nothing but it is a complex. It's a complex because the real part is present and the imaginary part is present. So the real part of the Cn is always even and the imaginary part of the Cn is always odd in nature. So this point also I have already told you. The next point is, so for f of t, if the Fourier series coefficient is Cn, then f of t plus t0 as a Fourier series coefficient Cn into e to the power of plus jn omega naught t0. Cn it is going to hold for an as well as Bn. So what this is for? Cn we are going to study. Cn concept is also going to hold for an and Bn. Suppose if it is a minus means, it is a minus means here also minus. So right here plus and here is a minus. So f of t means for f of t the Fourier series coefficient is Cn, and for f of t plus or minus t0 the Fourier series coefficient is Cn into e to the power of plus or minus jn omega naught t0. So same concept is also going to hold for an as well as Bn. So if f of t has a Fourier series coefficient Cn, then f of t plus or minus t0 has a Fourier series coefficient Cn into e to the power of plus or minus j n omega naught t0. So here plus means here plus, here minus means here also minus. Suppose if f1 of t has a Fourier series coefficient Cn1 and f2 of t has a Fourier series coefficient Cn2, then a1 into f1 of t has a Fourier series coefficient a1 into Cn1 and a2 into f2 of t has a Fourier series coefficient a2 into Cn2. Then the summation of these two things means you also have to do a summation of these two things. a1 into f1 of t plus a2 into f2 of t has a Fourier series coefficient a1 into Cn1 plus a2 into Cn2. So these things always you have to keep in your mind. So therefore we can say if f1 of t has a Fourier series coefficient Cn1, then f2 of t has a Fourier series coefficient Cn2, then a1 into f1 of t has a Fourier series coefficient a1 into Cn1 and a2 into f2 of t has a Fourier series coefficient a2 into Cn2, then addition of these two things will be the addition of these two things are here also. So a1 into f1 of t plus a2 into f2 of t has a Fourier series coefficient a1 into Cn1 plus a2 into Cn2. But what is the condition? The condition is very simple. f1 of t and f2 of t has the same time period. As same time period. So there is a point in between and as same time period. So both have the same time period. So both have the same time period. So both have the same time period. So I already told you, suppose if they are not same time period means on the same time period try to become the Fourier series coefficient and now go for the addition. So I already told you, if they have same time period means go for the like this. Suppose if they have different time period means go for the LCM of the time periods and now the common time period. So on this common time period, define the forces coefficient and then follow this procedure. So suppose if f of t has a forces coefficient Cn, then d by dt of f of t has a forces coefficient Jn omega naught into Cn. Then k the derivative of f of t has a forces coefficient Jn omega naught on the power of k into Cn. So you can say if f of t has a forces coefficient Cn, then d by dt of f of t has a forces coefficient J into n into omega naught into Cn. And k derivative of f of t has a forces coefficient Jn omega naught on the power of k into Cn. It is a very important thing. I already told this so many number of times. So therefore we can say that if f of t has a forces coefficient Cn, then d by dt of f of t has a forces coefficient Jn omega naught into Cn, and k the derivative of f of t has a forces coefficient Jn omega naught on the power of k into Cn. So these things always you have to keep in your mind. The next point that we are going to discuss, which is by expression of evaluation, we got the Cn, but not defined for few n. So by general procedure, find those values also. Listen carefully. By expression of evaluation, we got the value of Cn, but not defined for few n. So by general procedure, find these values also. So what is the meaning of this one? So you know Cn. What is the Cn? Cn is nothing but, I have already told you what is the value of Cn. Cn is equal to 1 by t integral over the 1 time period f of t into e to the power of minus j omega t into dt. I have already told you, right? Cn is equal to 1 by t equals to the 1 time period f of t into e to the power of minus jn omega naught t dt. So with the help of, so substitute the function f of t and do the integration of 1 time period, and we are going to get certain expression. So if you see this, suppose, let me assume we are going to get like this. So let me assume, so I am going to assume we are going to get like this example. So like this we have got. So from this what we can say, suppose if n is equal to 1, this value tends to, this value is there, it is becomes to infinity. So therefore what you have to do, for certain values of n it is not defined. So in that case what you have to do, so you have to go for the, again in place of n, substitute 1, c1 into 1 by t integration of the 1 time period f of t into e to the power of minus j omega naught t dt. In place of n I have substitute and then again do the integration and get those values. Means wherever this value is not defined, you have to separately again for those values of n. So let me assume it is, suppose we got like this n minus 1 into n minus 2 we got. Then we can say this c of n is not defined at n is equal to 1 and also at n is equal to 2. Then substitute in this case n is equal to 1 you substitute and simplify, you will get some value. Again you substitute n is equal to 2, again you simplify, you are going to get the value of c2. So this is a general expression, but this general expression is not defined for certain values of n. So if you want those values for what is the value of Cn for those values, so you have to substitute here and you simplify, we are going to get those values also. That is the meaning of this one. So therefore, by expression of evaluation, we are going to get the Cn, but it is not defined for 2n. So by general procedure, find these values also. So what is the meaning of this one? As I have already told you, basically, we can say in simple words. So with the help of Cn expression, we are going to simplify and we are going to get certain equation that we are going to get. But that equation is not defined for few values of n. So if you want to find for those values of n what is Cn, then substitute the general formula and simplify and get the value of Cn for those values also. So by expression of evaluation, we got the Cn, but it is not defined for few n. So by general procedure, find those values also. So now the next point is for OR signal. So for OR signal, what is going to happen? I have already told you what is the meaning of OR signal. OR signal means f of minus t is equal to minus of f of t. Then the signal is follows the OR signal. So for OR signal, a0 is equal to 0, an is equal to 0, and bn is not equal to 0. I have already told you, right? So now what is c0? C0 is equal to a0. And what is Cn? Cn is equal to an by 2 minus j pn by 2. As I already told you. So from this we can say Cn is equal to an by 2 minus j bn by 2. So now as an is equal to 0, so definitely Cn is nothing but purely imaginary. So therefore we can say C0 is nothing but 1 by t integration with the 1 time period f of t into e to the power of minus j n omega naught t. In place of n substitute 0, then we are going to get f of t dt. This is nothing but a0. So this value is equal to 0, as I've already told you. So what we can say, when the signal is an odd signal, then A naught is equal to 0 and AN is equal to 0 and BN is not equal to 0. So only some terms are going to present in a, all the sine terms are going to present in a trigonometric series. This term is absent and the cos terms are also absent. As AN is equal to 0, Cn is purely imaginary. And the next point is, if f of t is equal to minus of f of t plus or minus t by 2, then for this function f of t, Cn is equal to 0 or n is equal to even is called as the Orff symmetry because C naught is equal to A naught is equal to 0. So what is the meaning of this one? I have already told this point, let me discuss here. So I have already told you, suppose if f of t is equal to minus of t plus or minus t by 2, this is called as the odd Orff symmetry. Odd Orff symmetry means all the odd terms of the sine and cosine terms are going to get present. So all the odd frequencies of the sine term and the cos terms are going to get present. So what is the meaning of this one? We can say A naught is equal to 0. So AN and here BN. So I have already told you here. I have already told it's odd Orff symmetry. Odd Orff symmetry means what we can say. So odd Orff symmetry means only the odd harmonics of the all the cos terms and sine terms are going to get present. So AN is not equal to 0, for N is equal to 1, 3, 5, cosine. BN is also not equal to 0, for N is equal to 1, 3, 5. So only the odd harmonics are going to get present. So we can say, so we can also say in other fashion also, AN is equal to 0 for even values of N, BN is equal to 0 for even values of N also, we can say. Simply, right? So we can say AN not equal to 0 for odd values of N, BN not equal to 0 for odd values of N, or we can say AN is equal to 0 for even values of N and BN is equal to 0 for even values of N, we can say. So this is called as the odd Orff symmetry. So f of t is equal to minus of f of t plus or minus t by 2. If any signal is going to satisfy this property, then it is called as the odd Orff symmetry. So this point you have to keep in your mind. Then what is Cn? Cn, C naught is equal to A naught. Cn is nothing but An by 2 minus j Bn by 2. So definitely for even values of N, An is equal to 0 and Bn is equal to 0. So Cn is also equal to 0 for even values of N. So therefore we can say Cn is not equal to 0 for only odd values of N. So only for odd values of N. So this is what I am trying to tell you. So therefore we can say in the case of odd Orff symmetry, A naught is equal to 0 and An is not equal to 0 for odd values of N and Bn is not equal to 0 for odd values of N. And C naught is equal to A naught and Cn is equal to N by 2 minus j Bn by 2 and Cn is not equal to 0 for odd values of N. So Cn is not equal to 0 for odd values of N. So this point you have to keep in your mind. So therefore we can say that simply odd Orff symmetry means only the odd frequencies of the all the cos terms and the sine terms are going to present. Means only the odd harmonics of the sine terms and the cos terms are going to get present. And this term is absent and the even harmonics of the sine term and the cos terms are also absent. So this point always you have to keep in your mind. Same thing here, same thing. So when f of t is equal to minus of f of t plus or minus t by 2, then this is called as Orff symmetry. Then for this function I have already told you what is the meaning of this one. I have already told you only the odd harmonics are going to get present. So only the odd harmonics are going to get present. So this is called as the odd Orff symmetry. So therefore Cn is equal to 0 for even values of N or Cn is not equal to 0 for odd values of N. So what is the meaning of this one? I have already told you only the odd harmonics so only the odd harmonics of the sine terms, all the odd harmonics of sine terms and cos terms are going to be present and remaining everything is 0. So this point you have to keep in your mind. So now the next thing is from graph checking Orff symmetry. So from graph how to check whether the signal is Orff symmetry or not. See in one complete time period, divide the one complete time period into two equal halves. In this, one magnitude is positive and the other magnitude to be negative and equal. Then it is prone to the Orff symmetry. That signal f of t is going to happen. Basically, this is the odd Orff symmetry. So this is the odd Orff symmetry. So odd Orff symmetry. So basically, if you want me to give a small example, so you can say this is the best example. So this is the best example I can give you. right? C is going to get repeat. So this is a plus 1, this is a minus 1. So this is a t by 2 and this is the t. So suppose let me draw by this is f of t. This is f of t. Then what is f of t minus t by 2? You must shift the signal by t by 2 units. So how you are going to get? So you are going to get like this. So from this you are going to get. How to shift about t by 2 means it is going to repeat like this. So much it is going to repeat like this. Right? This is minus 1, this is plus 1. So again multiply by minus for this function. Multiply by minus. Then what we are going to get? We will multiply by minus 1. Then minus 1 will become plus 1 and plus 1 will become minus 1. So we are going to get like this again. So this is t by 2, this is t. So this is 1 and this is minus 1. So this is 1, this is minus 1. So same, these both are same, right? So these both are same. So therefore f of t is equal to minus of f of t minus t by 2. So therefore we can say this is a plus or minus. You go for anything. So this is called as the odd of-wave symmetry means see. So only see the one cycle. The one cycle, divide the cycle into two equal of parts. Into equal parts. T by 2 and T by 2. Here it's a plus 1 means here it should be minus 1. Those should be of same magnitude but of opposite side. Then only it is going to get satisfied. So f of t is equal to minus of f of t plus or minus t by 2 means whatever for the signal f of t, either you delay the signal by t by 2 or advance signal by t by 2, then multiply by minus, then you are going to get f of t. If that is the case, we say it is an odd of-wave symmetry. So see in one complete time period, divide the one complete period into two equal half. In this one magnitude is positive and the other magnitude to be negative equal, then it is going to behave like a odd of-wave symmetry. It is an odd of-wave symmetry. It is an odd of-wave symmetry. Odd of-wave symmetry for the signal f of t. Then I already told you what is C0. C0 is equal to A naught. And Cn, you know, A by 2 minus J, Vn by 2. I already told you. So now I have told you what is the meaning of odd signal. I have already told the meaning of even signal. And I have already told you what is the meaning of odd of-wave symmetry. So now with the help of this concept, we will move further. Suppose f of t is a real and even signal, then what is going to happen? Suppose if f of t is a real and even, then what is going to happen? I have already told you, if a signal is real and even means a0 is not equal to 0 and an is not equal to 0, but bn is equal to 0. Then what we can say? As a0 is not equal to 0 and an is not equal to 0, but bn is equal to 0 means a digit term is going to get present and all the cos terms are going to get present, but all the sign terms are absent. Then what is Cn? Cn is equal to n by 2 minus j bn by 2. See, if bn is equal to 0, then Cn is nothing but n by 2, which is the real. So Cn is purely real in nature. Now let's go for another thing. Suppose if f of t is a real as well as odd, then what is going to happen? Odd means, you know, f of minus t is equal to minus of f of t. Even means f of minus t is equal to f of t. I've already told you. So we can say, as f of t is a real and odd signal, so a0 is equal to 0 and an is equal to 0. So therefore, but bn is not equal to 0. So we can say a0 is equal to 0, an is equal to 0, but bn is not equal to 0. Which means the digit term is absent, all the cos terms are absent. Only all the sign terms are going to get present. If you substitute here, as an is equal to 0, then bn is not equal to 0. So only imaginary part is going to get present. So Cn is purely imaginary. It's purely imaginary. Now let's go for another thing. Suppose if f of 1 is the odd of-wave symmetry. Here I have to write here odd of-wave symmetry. Odd of-wave symmetry means I have already told you. Let me write here. Here even signal means f of minus t is equal to f of t. Here odd signal means f of minus t is equal to minus of f of t. Here odd of-wave symmetry. Specifically I have to say odd of-wave symmetry. Odd of-wave symmetry means f of t is equal to minus of f of t plus or minus t by t. This is follows odd of-wave symmetry. So I have already told you, in the case of odd of-wave symmetry, only the odd harmonics of the sine and cosine are going to get present. So only the odd harmonics of the sine and cosine are going to get present. So from this what we can say? Then we can say, so a0 is equal to 0 in this case because 0 is an even number. And an is not equal to 0 for odd values of n. And similarly, bn is not equal to 0 for odd values of n. So for odd values of n. So now you can see clearly, if an is not equal to 0 for odd values of n and bn is not equal to 0 for odd values of n, we can also say n is equal to 0 for even values of n, n is equal to 0 for even values of n also we can say. So Cn is equal to 0 for even values of n. Even values of n means n starting from 0, 0, 2 goes on. Or we can say Cn is not equal to 0 for odd values of n means n is equal to 1, 3, 5 and goes on. So an is equal to 0 for bn is equal to 0 for even values of n. Even values of n means n starting from 0. As I already told you. Even means you have to take from 0, odd means you have to take from 1. So what is C0? C0 is equal to A0. As if you substitute n is equal to 0. So C0 is equal to 0 means A0 is also equal to 0. So already I have given here. So therefore we can say only the odd harmonics of the sine and cosine are going to be present. DC term is absent. Even harmonics of the sine and cosine are also absent. The next thing is, if f of t is an even and odd wave symmetry, suppose if f of t is going to satisfy two properties, which is an even property as well as the odd half wave symmetry, then what is the meaning of this one? So f of minus t is equal to f of t even, and half wave symmetry, odd half wave symmetry means I already told you f of t is equal to minus of f of t plus or minus t by 2. If these both are satisfied, then what we can say? So let me write for the first property for the even what is going to happen. So even is a0 is not equal to 0, and an is not equal to 0, and bn is equal to 0. This is for the even. Odd half wave symmetry means I have already told you a0 is equal to 0 and an is not equal to 0 for even odd values of n, and bn is not equal to 0 for odd values of n. So now combine these two properties and tell me what is the overall properties. Here a0 is not equal to 0, here a0 is equal to 0. So from this we can say a0 is equal to 0. So a0 is equal to 0. Here n is not equal to 0 for all values of n. Here n is not equal to 0 for only odd values of n. So from this we can say that an is not equal to 0 for only odd values of n. An is not equal to 0 for only odd values of n. Only for odd values of n, and it is not equal to 0. Here bn is equal to 0 always. Bn is equal to 0 always. Here bn is not equal to 0 for only odd values of n. For odd values of n. So from this we can say bn is equal to 0 for all values of n. So bn is equal to 0. Bn is equal to 0 for all values of n. So if you see clearly, here a0 is not equal to 0, here a0 is equal to 0. So from this we can say a0 is equal to 0. Here an is not equal to 0 for all values of n. And here an is not equal to 0 for only odd values of n. So from this we can say that even values of n it is 0. Even values of n it is 0. So only for odd values of n it is not 0. N is not equal to 0 for odd values of n. Here bn is equal to 0 always. Here bn is not equal to 0 for only odd values of n. So if we combine, so definitely bn is equal to 0 for all values of n. You have to combine the properties. So from this what we can say? Here a0 is not equal to 0, here a0 is equal to 0 means it is equal to 0. Here n is not equal to 0 for all values of n, here n is not equal to 0 for only odd values of n. So therefore what we can say? So therefore n is not equal to 0 for only odd values of n. Here bn is equal to 0 always. Here bn is not equal to 0 for only odd values of n. So therefore it is equal to 0 for all values of n. So bn is equal to 0 for all values of n. So therefore bn is equal to 0 for all values of n, and a0 is equal to 0, and an is equal to 0 for n values of n, or we can say n is not equal to 0 for odd values of n, we can say. So from this we can say only odd cos terms are going to get present. So from this we can say these term is absent, all the sine terms are absent, and all the even cos terms are also absent. Only the odd harmonics of cos terms are going to get present. Now the next point is, if f of t is the odd signal as well as the odd half wave symmetry, then what is going to happen? If f of t is the odd as well as odd half wave symmetry. Odd means f of minus t is equal to minus of f of t. And half wave symmetry means odd half wave symmetry means f of t is equal to minus of f of t plus or minus t by 2. If these two are satisfied, then we can say this is going to satisfy the two properties. One is the odd property as well as the odd half wave symmetry. So in that case, what is going to happen? So let me write here. So odd means what I told you, odd means a0 is equal to 0, and an is equal to 0, and bn is not equal to 0 for odd. Suppose odd half wave symmetry means, what I told, odd half wave symmetry means only the odd harmonics are going to get present. Only the odd harmonics are going to present. So A naught is equal to 0 and An is not equal to 0 for odd values of n, and Bn is not equal to 0 for odd values of n, So now, if we combine these two properties, we can say here A naught is equal to 0, we can say A naught is equal to 0. So overall A naught is equal to 0. Here An is equal to 0 for all values of n. Here An is not equal to 0 for only odd values of n. So by default we can say n is equal to 0 always. An is equal to 0 always. Here Bn is not equal to 0 for all values of n. Here Bn is not equal to 0 for only odd values of n. Means Bn is equal to 0 for even values of n. So therefore Bn is not equal to 0 for odd values of n. So Bn is not equal to 0 for only odd values of n. So if you have to combine the properties, So from this we can say A naught is equal to 0, An is equal to 0, and Bn is equal to 0 for even values of n, or Bn is not equal to 0 for odd values of n. So therefore only odd or mix of sign terms are going to be present. So therefore we can say if a signal is going to satisfy both the odd property as well as the odd of phase symmetry, we can say only the odd harmonics of the sign terms are going to be present. Suppose if f of t is a real and a non-symmetric, it is not even signal, it is not a odd signal, it is not even satisfying any odd of phase symmetry, then we can say it is A naught is not equal to 0 generally, An is also not equal to 0 generally, so Bn is also not equal to generally. Therefore we can say A naught is not equal to 0 generally, An is not equal to 0 generally, and Bn is also not equal to 0 generally. So Cn is nothing but An by 2 minus j Bn by 2. As An is not equal to 0 and Bn is not equal to 0, so Cn is generally complex in nature. So if the signal it's a real signal, it is not having any symmetry. It is not symmetric, means it is not even signal, it is not odd signal, it is not even satisfying any order of phase symmetry, then definitely A naught is not equal to 0, An is not equal to 0, and Bn is not equal to 0. So definitely Cn will be complex in nature. This point you have to keep in your mind. Suppose for g of t, if the Fourier series coefficient is Cn, for a plus g of t, the Fourier series coefficient will be same Cn for n not equal to 0, and it is a plus c naught for n is equal to 0, because only the DC terms are going to get added, but the remaining terms are not going to get added. So only the DC terms are going to get added, but the remaining Fourier series coefficient will remain as it is. Only the DC part is going to get added for this constant way, and the remaining things will never get changes. So the Fourier series coefficient Cn for n not equal to 0, and is equal to a plus c naught for n is equal to 0. Only the constant part is going to get added. Only the constant Fourier series coefficient is going to get added, and the remaining things will never get added. So therefore, for this signal, the Fourier series coefficient is Cn for n not equal to 0, and is equal to c naught plus c for n is equal to 0. So this point you have to keep in your mind. The next point that we are going to discuss, which is power in the periodic signals in the terms of the Fourier series coefficients. So I am going to find what is the expression of the power in the periodic signals in terms of Fourier series coefficients. I have already told you all the periodic signals are power signals, because in the periodic signal the energy is equal to infinity and power is equal to finite. So these signals are called as a power signal. So all the periodic signals are called as a power signal, and I am going to find the expression of the power in the periodic signals in terms of the Fourier series coefficients. So I have already told you for a periodic signal f of t, we are going to represent the trigonometric Fourier series coefficient, which is a naught plus sigma n is equal to 1 to infinity an cos n omega naught t plus bn sin n omega naught t. So you know what is the power? Power is equal to integration of power is equal to energy by time. So I am going to find only the energy for one time period and time for the one time period. So integration over the 0 to t f of t equals to dt by t. So this is expression of the energy in one time period, and this is by corresponding time which is t. So then what we are going to get? So if you simplify, we are going to get like this. So we are going to get like this, which is basically a naught square plus sigma n is equal to 1 to infinity an square by 2 plus bn square by 2 that we are going to get. So if you simplify this one, finally we are going to get a naught square plus sigma n is equal to 1 to infinity an square by 2 plus bn square by 2. So what is the meaning of this one? So see, the only thing is very simple. Just to, for each and everything, just to find the RMS value and do the square, that's it. So for each and every coefficient, for each and every signal which is present here, just find the RMS value and do the square. So for A naught, this is signal, RMS value is A naught, so do the square of that one. Similarly, sigma n is equal to 1 to infinity. So what is the RMS value of a n cos n omega t? A n by root 2. So do the square of that one. We are going to be a n square by 2 plus for b n sin n omega t. What is the RMS value b n by root 2? So do the square of that one. We are going to get again a n square by 2. That's it. So this is called as the power. So this is called as the power. So the power which is going to present in a single f of which is a naught square plus sigma n is equal to 1 to infinity a n square by 2 plus b n square by 2. So these things always you have to keep in your mind. So what I have told you, I have told you very simple. For each and every component, find the RMS value and do the square. That's it. So therefore, for a naught, the RMS value is a naught. So do the square of that one, a naught square plus sigma n is equal to 1 to infinity. For a n cos n omega t, the RMS value is n by root 2. So do the square of that one, we are going to get n square by 2 plus for b n sin n omega t, the RMS value is b n by root 2. So do the square of that one, we are going to get b n square by 2. So therefore, we are going to get the power which is going to present in the signal f of t, which is a naught square plus sigma n is equal to 1 to infinity a n square by 2 plus b n square by 2. So this is in terms of the trigonometric Fourier series coefficients. Suppose if you want to write the expression in the terms of the exponential Fourier series coefficient is sigma n is equal to minus m to plus n mod of c of n whole square. So mod of c of n whole square. So this one you have to keep in your mind. So sigma n is equal to minus m to plus n mod of c of n whole square. So these things always you have to keep in your mind. So sigma n is equal to minus m to plus n mod of c of n whole square. So let me write the formula. So this formula you have to keep in your mind. So for a periodic signal f of t, the expression of the power is equal to a naught square plus sigma n is equal to 1 to infinity a n square by 2 plus b n square by 2. Or you can write in the other portion also, which is sigma n is equal to minus m to plus n by the mod of c of n whole square. So these two formulas you have to keep in your mind. So these two formulas always you have to keep in your mind. So now the next point is truncated Fourier series. So we are going to discuss the next concept, which is called as the truncated Fourier series. So what is the meaning of truncated Fourier series? Basically we have infinite number of terms, right? Instead of all this infinite number of terms, I will take only few terms. That is called truncated Fourier series. Means instead of taking this infinite number of terms, I will take only few terms. Then that is called as a truncated Fourier series. So simply f of t is for a naught plus sigma n is equal to 1 to infinity a n cos n omega naught t plus b n sin n omega naught t. So due to infinite terms, this cannot be realized. So here basically we have infinite number of terms. But physically, if you want to have infinite number of terms, it's a very severe pain in the neck. So practically, if you want to consider all the infinite number of terms, it will be a very severe pain in the neck. So therefore, due to infinite number of terms, this cannot be realized. So if you need a particular amount of power, use only those terms which can satisfy the required power. So if you need only a particular amount of power, use only those terms which can satisfy the required power. The new Fourier series is called as a truncated Fourier series. So now this can be physically realizable. So basically what I have to tell you is very simple. Say for this trigonometric Fourier series, we have infinite number of terms. If you have infinite number of terms, this physically cannot be realized. Suppose I want a signal of only some 2 units of power. So 2 units of power you can get with the help of some number of terms. So only those terms you have to include. Then it is physically realizable because we have only few number of terms. So it is physically realizable. So this is called the truncated Fourier series because we are going to include only few number of terms in a Fourier series. So because of this reason, it is called the truncated Fourier series. So if you need a particular amount of power, use only those terms which can satisfy the required power. So this new Fourier series, which is called the truncated Fourier series. So now this can be physically realizable. So in simple words, I can say like this. Basically, here in this Fourier series, you have infinite number of terms. If you have infinite number of terms, basically this cannot be realizable practically. So what I will do, suppose if I want some particular amount of power, so this particular amount of power you can get only with the help of few number of terms. So I will include only those number of terms. So because of this now, if you have few number of terms, we can practically realizable. So because of this reason only we can say we are obtaining only few number of terms. So that is why it is called truncated Fourier series. So if you need a particular amount of power, use only those terms which can satisfy the required power. And the new Fourier series is called as the Talking to Fourier series. So now this can be physically realizable. So now the next point is power in the nth harmonic component is Pn. What is the Pn? So what is the power in the nth harmonic component is Pn. So what is Pn? Pn is nothing but nth harmonic component. So nth harmonic component means suppose in the trigonometric Fourier series, what is the nth harmonic component? Suppose in the trigonometric Fourier series, what is the nth harmonic component? An cos n omega naught t plus Bn sin n omega naught t. This is the nth harmonic component. So take the power of this one. RMS value n by root 2 whole square. Sorry, RMS value is n by root 2. So the square of the thing we are going to n square by 2 plus RMS value of Bn is Bn by root 2. So the square of the thing we are going to get Bn square by 2. So this is called as the nth harmonic power. So this is called as the nth harmonic power. So this is the power which is present in the nth harmonic component. So this is called as the power which is present in the nth harmonic component. So I have already told you. So this is the nth harmonic component in the trigonometric Fourier series. So you want to calculate what is the power which is present in the nth harmonic component, which is the RMS value whole square plus RMS value whole square, which is Bn square by 2 plus Bn square by 2. So this is the amount of power which is present in the nth harmonic component. So this is the amount of power which is present in the nth harmonic component, An square by 2 plus Bn square by 2. So finally I can say this is the nth harmonic component in the trigonometric Fourier series. So in this form I want to find what is the amount of power which is present. Then it is called as the nth harmonic power, which is the RMS value whole square plus RMS value whole square, which is n by root 2 whole square plus n by root 2 whole square, Bn by root 2 whole square, which is nothing but n square by 2 plus Bn square by 2. So this is called as the power which is going to present in the nth harmonic component. Suppose in the exponential format, suppose in the exponential trigonometric series means what is the nth harmonic component? The nth harmonic component we are going to get two things, which is C minus n e to the power of minus j n omega naught t and Cn e to the power of plus j n omega naught t. So two terms we are going to get. These are the two terms that we are going to get for a corresponding frequency. So here what is the power? The power is mod of C of minus n whole square plus mod of C of n whole square. And I already told you mod of Cn is always equal to mod of C of minus n. But the modules are same, so it will become two terms of mod of C of n whole square. So that is the reason. This is the amount of power which is going to present in the nth harmonic component in the exponential Fourier series. So this is the amount of power which is going to present in the nth harmonic component in the trigonometric Fourier series, and this is going to present in the amount of power which is going to present in the nth harmonic component of the exponential Fourier series, and both are equal. So both are equal. This is nothing but we can write finally the amount of power which is going to present in the nth harmonic component is equal to An square by 2 plus Bn square by 2. This is from the trigonometric Fourier series, and this is nothing but two terms of mod of C of n. So you know what is mod of Cn, you know, An by 2 minus j Bn by 2, you know, right? So what is mod of Cn? Mod of Cn is under root of An by 2 whole square plus Bn by 2 whole square. So do the square of that one. The square means mod of Cn whole square is equal to An square by 4 plus Bn square by 4. So multiply the 2 on both sides, then what we are going to get? It is nothing but An square by 2 plus Bn square by 2. So this is nothing but same, but are equal. So that is the reason I have written. So therefore, the amount of power which is present in an nth harmonic component is equal to An square by 2 plus Bn square by 2, which is equal to 2 times of mod of C of n whole square. This is because of the trigonometric Fourier series coefficients, and this is because of the exponential Fourier series coefficients. So this point always you have to keep in your mind. So for any signal, as the name indicates, the modulus of the amount of the signal is going to be decreases. Yes, this point is same. This point is very simple. See, as the value of n increases, see, as n increases, An is going to get decreases, Bn is also going to get decreases, so Cn is also going to get decreases. So what I can say, very simply, I can say, if you take a magnitude, so we can say that the Fourier series coefficient magnitude value, they are going to get decrease. So as the value of n increases, the value of the Fourier series coefficients, they are going to get decreases. Either the trigonometric Fourier series coefficients or the exponential Fourier series coefficient, their magnitude are going to get decreased. So therefore we can say for any signal or for any periodic signal, as the value of n increases, the magnitude of the Fourier series coefficient, they are going to get decreases. And most of the power is going to present only in the first few harmonics. See, as you can see clearly, as the value of n increases, the amount of Cn decreases means An decreases, Bn decreases. As An decreases, Bn decreases, then RMS value is also going to get decreases. So most of the power is going to get only in the only few number of harmonic. The first few harmonic terms only you are going to get. So most of the power is going to present only few harmonic. The first few harmonics only we are going to get. So most of the power is going to present only in the first few harmonics only. So what I can say very simply, so most of the power is going to present only in the first few harmonics only. So most of the power is going to present only in the first few harmonics itself. So most of the power is going to present only in the first few harmonics itself, because I've already told you, as the n increases means harmonic number increases, then definitely the Fourier coefficient value they are going to decreases means their power is also going to decrease, because RMS value by whole square, RMS value whole square means as the Fourier coefficient decreases, the RMS value decreases, RMS is also going to get decreases means power is also going to get decreases. So most of the power is going to present only in the first few harmonics itself. The next thing is, if f of t is a real value signal, then C of n is equal to C of minus n conjugate, or vice versa is also true. What is Cn conjugate is nothing but C of minus n. But suppose if f of t is a complex value signal, then this is not valid. This is not valid. So see, basically whatever the thing that we have learned for a real signal only, whatever the as we basically I have given the trigonometric Fourier series, and I have given the trigonometric Fourier series with Cn plus sigma n is equal to 1 to infinity An cos n omega naught t plus Bn sin n omega naught t, and this is the trigonometric Fourier series coefficient, the trigonometric Fourier series, and exponential Fourier series sigma n is equal to minus n plus infinity Cn into e to the power of Jn omega naught t. So this is a exponential Fourier series. So basically, it's a trigonometric Fourier series and this is the exponential Fourier series. So this basically we have defined this concept for real signal. So basically here, whatever this concept is valid for only the real signals. Only for real signals only we have discussed this concept. So this is valid only for the real signal. And we have learned one concept. Cn is equal to An by 2 minus j Bn by 2. We already told it. And C of minus n we are going to get An by 2 plus j Bn by 2 we are going to get. From this we can say Cn is equal to C minus n conjugate, or vice versa is also true. Cn conjugate is equal to C of minus n. I have already told you. So this concept is going to hold only for the real signals only. Only for real signals. So for complex signals, these are not valid. So for complex signals, what is going to happen? This concept is invalid. So for complex signal, this concept is invalid because Cn is not equal to C of minus n conjugate, or Cn conjugate is not equal to C of minus n. So this point you have this to keep in mind. So Cn is equal to C minus n conjugate. Cn conjugate is equal to C of minus n. This concept is applied for only real value signals. And Cn is not equal to C of minus n conjugate. And Cn conjugate is not equal to C of minus n. This concept is for the complex signal. Therefore, whatever this concept is valid only for the real signals, and these are invalid for the complex value signals. So this concept is valid only for the real value signals, and this concept is invalid for the complex value signals. Same thing we have discussed here. So therefore we can say here this concept is applicable for only real value signal, and this concept is invalid for the complex value signals. This point you have to keep in your mind. So now the next point is, suppose if f of t is a real value signal and even, then what is going to happen? As I already told you, when f of t is a real value signal and even, then what is the thing I have already discussed? If f of t is a real value signal and also even, then a0 is not equal to 0, an is not equal to 0, and bn is equal to 0. So Cn is equal to n by 2 minus j bn by 2, as bn is equal to 0 and an is not equal to 0, so Cn is purely real. Suppose if f of t is a real value signal and odd, so f of t is a real value signal and odd, then what is going to happen? See, when f of t is a real value signal and odd means a0 is equal to 0, an is equal to 0, and bn is not equal to 0, and Cn is equal to n by 2 minus j bn by 2, as an is equal to 0 and bn is not equal to 0, so Cn is purely imaginary. Suppose if f of t is a real value signal, means it is not having any symmetry, it is not a even value signal or not odd value signal, a0 is not equal to 0, n is not equal to 0, and bn is not equal to 0. So Cn is equal to n by 2 minus j into bn by 2, as n is not equal to 0, bn is not equal to 0. So therefore Cn is generally complex in nature, means the real part is present and the imagined part is also present. Then what is going to happen? I already told you Cn conjugate is equal to C of minus n, and the vice versa is also true, which is Cn is equal to C of minus n conjugate. Both are true. So here f of t is called as neither even signal nor odd signal. I already told you this concept, right? This concept is valid only for the real value signals only for the real value signal, and this concept is invalid for the complex value signals. So now the next point is Cn is not equal to 0 for minus n1 to n0. Where n is lying from minus n1 to n0. If f of t is a complex signal, whereas Cn is not equal to 0 minus n0 to n0 if f of t is a real signal. See, these range are same. If this range are same, means it is a real value signal. If this range are different, means it is a complex value signal. Suppose in the question they are given a Cn is not equal to 0 for some range of n. The range should be basically what I can say. Listen carefully, as I've already told you. Suppose Cn is nothing but C of minus n conjugate, right? And Cn conjugate is equal to C of minus n. Suppose I am going to assume that C1 is not equal to 0. Then I will try to find what is C of minus 1. I will try to find. So C of 1 is equal to C of minus 1 conjugate. What is the complex conjugate on both sides? C1 conjugate is equal to C of minus 1. See, as C1 is not equal to 0, C of minus 1 is also not equal to 0. So therefore, as T1 is not equal to 0, so C of minus 1 is also not equal to 0. Suppose if C of 2 is not equal to 0, then definitely C of minus 2 is also not equal to 0. Suppose if C of 3 is not equal to 0, then C of minus 3 is also not equal to 0. So what I can say in simple words that if C of n is not equal to 0, then definitely C of minus n is also not equal to 0. So what we can say, suppose from minus n0 to plus n0, if Cn is not equal to 0, means for n0 if it is not equal to 0, means for minus n also, for minus n also it is not equal to 0. Then only we can say the signal is said to be real signal. But if the range is different, means it is a complex value signal. If the range is same, means it is a real value signal, and if the range is different, means it is a complex value signal. So suppose here, suppose minus n1 less than or equal to n less than or equal to suppose n2. Here n1 is not equal to n2. So in that case, it is called a complex value signal. It is called the complex value signal. If both are same, means it is a real value signal. So finally, I can say if C of n is not equal to 0, C of minus n is also not equal to 0 based on the concept. So therefore, if C of 2 is not equal to 0, C of minus 2 is also not equal to 0 for a real value signal. But this is not the truth. But this is not the truth for the complex value signal, because I've already told you this concept is invalid for the complex value signal. So because of that reason, that suppose for complex value signal, suppose if C of minus 1 it is not equal to 0, then C of minus 1 can be equal to 0 or may not be not equal to 0 also. It can be or it may not be. We don't know. But this compulsory we don't know. So that is the reason I already told you C of n is equal to C of minus n and C of conjugate is equal to C of minus n. So this concept is only for the real value signal. And the C of n is not equal to C of minus n conjugate, and C of n conjugate is not equal to C of minus 1 for the complex value signal. So therefore, if here we can say here, if C of 1 is not equal to 0, then C of minus 1 is also not equal to 0. Suppose here, if C of 1 is not equal to 0, then C of minus 1 it can be equal to 0 or it may not be equal to 0. We don't know practically what will happen. So that is the reason. If they both have the same values of n, then we say it is a real value signal. If the values of n are different, one is a plus 2 and the other is a 6 plus 6 means it is a complex value signal. Therefore, we can say that if see here n0 and n0 both are same, so here plus n0, here minus n0, then only we can say it is a real value signal. If these both are the different values of n, then it is a complex value signal. The next thing is shifting and reversal of f of t won't affect the time period of f of t. So shifting and reversal of f of t won't affect the time period of f of t. See, only scaling is going to affect the time period of a signal f of t. But shifting and reversal means shifting is just you are moving a signal to the left or right. And reversal means just you are moving image. So by that two things, the time period will not change. Only with the help of time scaling. Only with the help of time scaling only the time period is going to get changed. But if you do the time reversal or the time shifting, by these two things, the time rate won't change. So by shifting property and time reversal property, time rate won't get affected. But by time scaling, the time rate is going to get affected. So now the next point is, suppose if f of t is equal to f of minus t, then I already told you this is called as a real even value signal or a real even value signal. Then what is going to happen? I already told you, if it's a real even value signal, then a0 is not equal to 0 and am is not equal to 0, but bn is equal to 0 means bc term and all the cost terms are going to be present. So f of t will have only the base term and all the cost assigned terms. Suppose if f of t is equal to minus of f of minus t, then this is called the real value or signal. Then a0 is equal to 0, an is equal to 0 and bn is not equal to 0. So in that case, the basic term is absent, all the cost terms are absent, only all the sign terms are going to get present. So f of t will have only all the sign terms. Suppose if f of t is equal to minus of f of t plus minus t by 2, then this is called the odd half-wave symmetry. As I already told you, this is called the odd half-wave symmetry. Odd half-wave symmetry means, see, listen carefully. Here there is a minus, here also there is a minus. So the shortcut to remember, here minus means is odd, here also odd, like that. It's odd half-wave symmetry. As I already told in the case of odd half-wave symmetry, only the odd elements of the sign and the odd elements of cos are going to be present. So therefore we can say Cn is equal to 0 for even values of n means Cn is not equal to 0 for odd values of n also we can write. So Cn is not equal to 0 for odd values of n. For odd values of n means all the odd harmonics of the sine and odd harmonics of the cos are going to get present. So there is no basic term. Basic term is nothing but n is equal to 0. N is equal to 0 is even. So basic term is also equal to 0. Suppose if f of t is equal to plus say of f of t plus or minus t by 2, then this is called the even half-wave symmetry. Because I have already told here is also plus, here also plus. So here even means it plus, here also plus. That is the reason here it is called the even half-wave symmetry. Then what is going to happen? For even half-wave symmetry, only the even harmonics of the sine and even harmonics of the cos are going to get present. Means Cn is equal to 0 for odd values of n. So therefore what is the meaning of this one? If Cn is equal to 0 for odd values of n means Cn is not equal to 0 for even values of n or even values of n. So Cn is not equal to 0 for even values of n means the basic term is present and all the even harmonics of the sine and cos are going to get present and also basic term is also going to get present. So therefore we can say simply, if the signal is even half-wave symmetry means all the even harmonics of the sine and even harmonics of the cos and also basic term, because n is equal to 0 is nothing but even number, right? N is equal to 0 is an even number. So therefore we can say as n is equal to even number means simply we can say that n is equal to 0 means it's an even number means base is also present. So therefore in the case of this property, even half-wave symmetry means all the even harmonics of the sine and cos are going to get present. Even means n is equal to 0, 2, 4 like that. N is equal to 0 means the DC part is also going to get present. So Cn is not equal to 0 for even values of n. So this part always you have to keep in your mind. Now the next point is, for any general signal f of t, the Fourier series coefficient magnitude keeps on decreasing with the increasing value of n generally. This point just now we have discussed that. So as the value of n increases, the magnitude of the Fourier series coefficient, either it is a trigonometric Fourier series coefficient or the exponential Fourier series coefficient, as the value of n increases, these values are going to get decreases. So for any general periodic signal f of t, the Fourier series coefficient magnitude keeps on decreasing with the increasing value of n generally. So this point I have already told you. So further I can say, as the value of n increases, means as the value of the n increases, the magnitude of the trigonometric Fourier series coefficient or the magnitude of the exponential Fourier series coefficient keeps on decreasing. So now the next point is 1 by j. See 1 by j, how I can represent this is a rectangular format. So how can I represent the polar format? So 1 by j means I can write like this. So 1 means I can write in a polar format 1 at an angle of 0 degree. And j means 1 at an angle of 90 degree. So if we simplify, this 90 goes upward, we are going to get 1 at an angle of minus 10 degree or 1 at an angle of minus 5 by 2 degree radians. So we can see here, or we can do it in other fashion also. Multiply and divide by j, then what are you going to get? J by j square. J square is equal to minus 1. So minus j we are going to get. So minus j, I can write like this, e to the power of minus j by 2 I can write, which is magnitude is equal to 1. And if we sum plus minus pi by 2, See, you can write in different fashion. Whether you can do write to the polar format or you do rationalization and then you can figure out the base value. Anything you can figure out. So as I already told you one important point. See, some books they are going to write in a polar format like this. Some books they are going to write like this. And some other books they are going to like this, like this. And the concept is same, which is nothing but r into cos theta plus I sin theta. So this is a general fashion. You can write in any fashion. Let's still the concept is same. Either you can write r into theta or r into e to the power of j theta. Any the concept is same, which is r into cos theta plus I sin theta. So minus 1 by j. How we can write minus 1 by j? So minus 1 by j means how can I write? So minus 1 means I can write like this. 1 at an angle of 180 degree. While j is something of 1 at an angle of 90 degree. So you simplify what you are going to get. 180 minus 90 is equal to 90 degree. So 1 at an angle of 90 degree you can write. Or simply do the ratio with respect to j by j. So minus j by j is nothing but minus cancels. So you are going to get plus j. So plus j is nothing but 1 at an angle of pi by 2 or 1 at an angle of 90 degrees. Either you can make 1 at an angle of 90 degrees or 1 at an angle of pi by 2 degrees or 1 into e to the power of j pi by 2. You can write anything. Similarly, e to the power of phi theta. E to the power of phi theta means I already told you the magnitude of the e to the power of phi theta is 1 because the magnitude is under root over cos theta plus sin square square. So under root over cos theta plus sin square theta. So definitely we can say its value is equal to 1. The magnitude is 1 and angle is theta because the magnitude of the e to the power of phi theta is nothing but 1 and this angle is theta. So we can write like this. So now suppose a1 into f of t plus a2 into g of t. See, suppose f of t has the Fourier series coefficient Cn and g of t has the Fourier series coefficient Dn. Listen carefully. If f of t has a Fourier series coefficient Cn and g of t has the Fourier series coefficient Dn, same thing everything here. So f of t has the Fourier series coefficient Cn is defined on a period of t1 and g of t has the Fourier series coefficient Dn is defined on a time period of t2. So these both are not same. Then what we have to do? What we have to do is basically we need to basically define on the same time period. We need to define on the same time period. But if you see clearly, these are two independent points. So here f of t has a Fourier coefficient Cn and g of t has a Fourier coefficient Dn. See, both have the same amount of time period. So both have the same amount of time period. Then if you take a sigma, which is a linear combination of the sigma, which is a1 into f of t plus a2 into g of t, which has a Fourier coefficient a1 into Cn plus a2 into Dn. F of t and g of t has the same time period. Suppose if they have different time period, then what will happen? Suppose if f of t has the Fourier coefficient Cn, which is defined on the time period t1, and g of t, which is as a Fourier coefficient Dn, which is defined for the time period t2. Suppose if they are not same, then what we have to do? If they are not same, then what we have to do is simply, what we have to do is very simple. First we have to take a common time period, which is LCM of t1, t2. So based on this two time period, we have to find what is the Fourier coefficient of Cn and the Fourier coefficient of g of t. So based on this two time period, the Fourier coefficient of f of t is Cn dash and the Fourier coefficient of g of t is Dn dash. So based on this common time period t. So now if you do the linear combination of these two things, it is nothing but the linear combination of these two things. Which is a1 into f of t plus a2 into g of t. Then we can say that they have the Fourier coefficient, which is a1 into Cn dash plus a2 into Dn dash. Now both have the same time period, which is nothing but t. So here let me write this as a t. So now I can write this. Basically now they have the same time period. So now they have the same time period, which is t and a t. So very simple. First thing is you have to define on the same time period. So first you have to define on the common time period. Then only you have to do the linear combination. So first thing is you have to define the Fourier coefficient on the same time period, and then you have to go for the linear combination. Otherwise, you don't have to go. So this is a very important point. So therefore, suppose if they have same time period, means directly go for the linear combination. If they have different time period, means now define on the same time period, define the Fourier coefficient, and then with respect to these Fourier coefficient, now you can go for the linear combination. So whatever the common time period is, the LCM of the T1 and T2. So this point always you have to keep in your mind. So finally I can say, if f of t has the Fourier coefficient Cn and if g of t has the Fourier coefficient Dn and both have the same time period, then they have to go for the linear combination, which is a1 into f1 of a1 into f of t plus a2 into g of t is nothing but it has the Fourier coefficient a1 into Cn plus a2 into Dn. Suppose if f of t has the Fourier coefficient Cn and g of t has the Fourier coefficient Dn, but these are different on the different time periods. F of t has the time period of t1 and g of t is at time period b2. So both are different time period, but they have to differ on the common time period by taking the time period as the LCM of t1 and t2. So based on this new time period, we have defined the new Fourier coefficient of f of t Cn dash, new Fourier coefficient of g of t is Dn dash. So now go for the linear combination, which is a1 into f of t plus a2 into g of t. Now we'll have the Fourier coefficient is 7 into Cn dash plus a2 into Dn dash. So this is the point always you have to keep in your mind. So now let's go for the another point. Dirichlet conditions for existence of the Fourier series. So Dirichlet conditions for the existence of the Fourier series. So what is the Dirichlet conditions for the existence of the Fourier series? See, I already told this point, but let me again repeat. So basically there are some Dirichlet conditions. So there are some Dirichlet conditions. If these Dirichlet conditions are satisfied, then compulsory the Fourier transform will exist. Sometimes these Dirichlet conditions are not satisfied, even though sometimes the Fourier series may exist or it may not exist. So this point I have already told you. Suppose if any signal, if it is satisfying all the Dirichlet conditions, definitely for the signal the Fourier series expression will definitely exist. Suppose if at least one of these Dirichlet conditions is not satisfied by any signal, sometimes the Fourier series may exist or it may not exist. This point I already told you, right? So here, what are the Dirichlet conditions? Signal f of t must be absolutely integrable in one of its time period, which is integration with over one time period mod of f of t dt is equal to finite. Means the signal must be absolutely integrable in one of its time period. There must be only finite number of maxima and minima in a given time period. There must be finite jump of finite discontinuous in a given time period. So there must be finite jump or finite discontinuous. There should be finite jump or finite discontinuous in a given time period. So there must be finite jump or we can say R. So R finite discontinuous in a given time period. So I already told you these are the three Dirichlet conditions. These are the three Dirichlet conditions. So what are those three Dirichlet conditions? The signal f of t should be absolutely integrable in one of its time period, and there must be only finite number of maxima and a minima in a given time period, and there must be finite jump or finite discontinuous in a given time period. So these are the three Dirichlet conditions. So what are the Dirichlet conditions? The signal f of t should be absolutely integrable in one of its time period. This induced of the one time period mod of f of t dt should give a finite value, and there must be only finite number of maxima and a finite number of minima in a given time period, and also there must be finite jump or the finite discontinuous in a given time period. If all these conditions are satisfied, then the Fourier series expression is going to valid for the signal f of t. Suppose if any of these Dirichlet conditions is not satisfied, still the Fourier series may exist or it may not exist. This point already I already told you. So if the Dirichlet conditions, if all the Dirichlet conditions are satisfied, then compulsory the Fourier series expression of Fourier signal will exist. Sometimes if the Dirichlet conditions may be satisfied or means all of them, so at least one of them is not satisfied. Let me say again, at least one of these cases not satisfied, still the Fourier series may exist or it may not exist. If any signal sufficiently satisfies all the three conditions, then compulsory Fourier series exists. These conditions are only sufficient conditions for the existence of the Fourier series, but not necessary conditions. I have already told you this point. So this is a point we have to remember. Dirichlet conditions, Fourier series. Suppose if all the Dirichlet conditions are satisfied, means compulsory the Fourier series expression of the signal will exist. Suppose if at least one of the Dirichlet conditions is not satisfied, then the Fourier series may exist or it may not exist. So this point already I have told you, right? So these 2 points always you have to keep in your mind. So these are not the necessary conditions. These are the sufficient conditions only. These are not the necessary conditions. Necessary means compulsory they have to satisfy, then only the Fourier series exists. But here, even though they are not satisfied, still the Fourier series is existing. That is the reason we say these are the sufficient conditions but not the necessary conditions. So if any signal sufficiently satisfies all the three conditions, then compulsory Fourier series exists. These conditions are only the sufficient conditions for the existence of the Fourier series, but not the necessary conditions. So therefore we can say that if all the distinct conditions are satisfied, then compulsory the Fourier series expression of any signal will exist. Even though even at least one of the distinct conditions if it is not satisfied, then the Fourier series may exist or it may not exist. This point you have to keep in mind. That is the reason distinct conditions are the sufficient conditions but not the necessary conditions for the existence of the Fourier series for a given periodic signal. The next point is Fourier series is applicable for only the periodic signals, and we are going to get Cn in a discrete nature. Why? Why it is because here n is only integers in the case of Fourier series. In the case of the Fourier series, we are going to have the Fourier series coefficient which is defined for only discrete value of n. N is the integers. That is the reason we say Cn is the discrete nature because n is the integer. Whereas the Fourier transform is applicable for the periodic signals, and here Cn is applicable. Cn is applicable omega here. We can say omega. Omega is a continuous nature. Here omega is a real number. So that is the reason we can say f of omega. F of omega means we can say it is defined for each and every value of omega. So that is the reason it has a continuous nature. So therefore we can say Fourier series is applicable for the periodic signals. Fourier series is applicable for the periodic signals. And in this case, we have the Fourier series coefficient which are defined only for the discrete values of n. So therefore, the Cn is also defined for only discrete value of n from n is equal to minus n to plus n to t. So because of this reason, the Cn is discrete nature. Whereas the Fourier transform is applicable for the periodic signals. And here, f of omega is a continuous signal because omega is a omega is a real number. So it is a continuous. So f of omega is nothing but a continuous. Basically here I have to write here f of omega, not the Cn. I should write here f of omega. Here f of omega I should write here f of omega. F of omega is a continuous nature. Here Cn is a discrete nature. Here I should write f of omega is a continuous nature, whereas Cn is a discrete nature. Here Cn we are going to consider, and here f of omega we are going to consider. So finally I can say Fourier series is applicable for the periodic signals, and here the Fourier series coefficients are defined for one discrete value of n. Cn is from minus n to plus n t, n is going to take only the integer. So definitely Cn is a discrete nature because it is defined only for particular values of integer values of n. Whereas the Fourier transform is applicable for the aperiodic signal. It's not a periodic. And here omega is a real number. It can take any value 0.001 also. So f of omega is nothing but it is also continuous nature. Means the magnitude is a continuous spectrum and the phase angle is also continuous spectrum because omega is a real number. So here you should write f of omega and you should write f of omega but not Cn. So now we will discuss one more point which is the Fourier transform. I already have told you the Fourier transform is applicable for the aperiodic signal. So f of omega is equal to integration of t is equal to minus into plus into f of t into e to the power of minus j omega t into dt. So this is the Fourier transform of the signal f of t. So if you want to write the reverse, then I will tell you f of t is equal to 1 by 2 pi integration over the omega is equal to minus into plus into f of omega into e to the power of air minus means air plus into d omega. So this point I have already told so many number of times. So f of omega is equal to integration of t is equal to minus into plus into f of t into e to the power of minus j omega t into dt. And f of t is equal to 1 by 2 pi integration over the omega is equal to minus into plus into f of omega into e to the power of plus j omega t into d omega. Here minus means here plus. These two formulas already I have told you. Suppose if you know f of t, if you substitute here, you are going to get the f of omega. Suppose if you know f of omega and if you substitute here, then we can get the value of the f of t, vice versa. So these two formulas always you have to keep in your mind. So f of omega is equal to integration over t is equal to minus into plus into f of t into e to the power of minus j omega t dt. And f of t is equal to 1 by 2 pi integration over the omega is equal to minus into plus into f of omega into e to the power of j omega t into d omega. So these 2 points always you have to keep in your mind. Now the next point is for any real signal f of t and f of t is a aperiodic signal, then f of omega is compulsory even conjugate. So what is the meaning of this one? Suppose if you take some real signal f of t and it's also a periodic signal, then The Fourier transform of that is going to satisfy this property, which is f of omega is equal to f of minus omega whole conjugate. This is what I already told you, right? Suppose you can say f of omega, it has some real part and the imaginary part. I already told you. So f of omega, if the real part is even conjugate, and the imaginary part is odd conjugate. I already told you, right? So this is odd conjugate. So odd conjugate. Yep, we are going to have the imaginary part. Suppose f of minus omega. F of minus omega is this is even, and this is also minus omega plus j of odd conjugate of minus omega. So definitely this is the even part and this is the odd part. So this is the even part and this is the odd part. So it will become again f even of omega. So it will become minus j f odd of omega. So this part I already told you. So f of minus omega. So what is this nothing but f of omega whole conjugate. F of omega whole conjugate. That's it. So f of minus omega is equal to f of omega whole conjugate. Vice versa is also true, which is f of minus omega whole conjugate is equal to f of omega also we will say. Because I have already told you, f of omega it has the real part and the imaginary part. Real part is the even nature and the imaginary part is the odd nature. As I have already told you, the real part is the even part and the imaginary part is odd part. So 3 plus omega by minus omega is will remain as it is, but this will be minus of. So this is nothing but f of minus omega is nothing but f of omega whole conjugate. So with the conjugate on the both sides, so again we are going to get f conjugate of minus omega is equal to f of omega. So this point we have to keep in your mind. That is the reason for any real signal f of t, and f of t is a aperiodic signal, then f of omega is nothing but a compulsory even conjugate, which is f of minus omega is equal to f conjugate omega, or f of omega is equal to f of minus omega whole conjugate. This point already have proved also. For any real signal f of t, and when f of t is a periodic signal and it is an even signal, then f of omega is a purely real. So purely real. So what is going to happen? Suppose if it is a purely real, what is the meaning of this one? If it is a purely real means for this part is only going to get present. So as f of t is a real signal, if f of t is the real signal and is an even part, then this will be no this part. So this part will be not there. So this will be not there. So in that case we can say f of minus omega is equal to f of omega only. So therefore we can say that suppose f of omega, so f of omega is nothing but there is only even part, because when f of t is a real signal and is also even nature, then only the real part is going to get present but not the imaginary part. So in this case what is going to happen? You can say f of minus omega is equal to f of omega minus omega, which is nothing but the even part of omega. It is nothing but f of omega itself. So f of minus omega is equal to f of omega. So therefore we can say anything we have written here. So same thing we have written f of minus omega is equal to f of omega. So when f of t is a real signal and a periodic signal and is a even signal, then f of omega is a purely real. For any real signal f of t, and when f of t is a periodic signal and it is an odd signal, then f of omega is a purely imaginary. It is a purely imaginary. So in that case what is going to happen? Suppose if f of t is a real signal and also a periodic signal and also an odd signal, only the imaginary part is going to get present. Only this part is going to get present. Then in that case what is going to happen? So you can say f of omega is equal to j times of f odd of omega. So replace omega, replace omega by minus omega, then we are going to get like this, right? So odd part of minus omega is nothing but plus of minus j f of odd of omega. So this is something that simply we can say that minus of f of omega. So this is minus of f of omega. So f of minus omega is equal to minus of f of omega for the odd part, and f of minus omega is equal to f of omega for the real part. If f of t is a even signal, generally this is the case. This is the general case. So you can say clearly these things always you have to keep in mind. So further I can say generally if f of t is a real signal as well as a periodic signal, then definitely we can say f of omega is equal to f of minus omega whole conjugate, or vice versa is also true, which is f conjugate of omega is equal to f of minus omega. And I already told you one point. So and I already told you one point, which is basically in the case of f of omega it's a complex number, the real part is even and imaginary part is odd nature. Suppose if f of t is a real signal and a periodic signal and also even signal, then f of omega is a purely. In that case f of omega is equal to f of minus omega. Suppose if f of t is a real signal and a periodic signal and is an odd signal, then f of omega is a purely imaginary. So in that case, f of omega is equal to minus of f of minus omega. This you can easily derive. And these things you can derive from the concept. So I want to remember only one thing, which is if f of t is a real signal and a periodic signal, then f of omega is nothing but it has a even part as well as the odd part. It has the even part as well as the odd part. So as a real part is even, that is the reason it is called as an even conjugate, because the real part is even. That is the reason the real part is even. That is the reason it is called as an even conjugate. Suppose if the real part is odd, means it is called as an odd conjugate. I have already told you, right? If the real part is even, means it is called as an even conjugate. If the real part is odd, means it is called as an odd conjugate. This is what I have already told you. That is the reason f of omega is called even conjugate, because the real part is even. In that case, to become f of minus omega is equal to f of omega whole conjugate, or f conjugate of minus omega is equal to f of omega. If f of t is a real and a periodic and even signal, then f of omega is a purely real. If suppose f of omega, if f of t is a real and a periodic and all signal, then f of omega is a purely imaginary. This point already I have told you. Suppose only when f of t is a real valued signal, then what is going to happen? See, only when f of t is a real valued signal, and I have already told you, for f of t, what is the Fourier transform f of omega, and f of minus t. F of minus t means what is the Fourier transform to become f of minus omega. This point I have already told you. One important point I have already told you. F of at. So f of at has a Fourier transform, which is 1 by mod a f of omega by a. A is equal to minus 1. So 1 by minus 1 minus equal to 1. Then f of minus omega. So f of minus t, Fourier transform is f of minus omega, and f of minus omega, f conjugate of omega. So f of minus omega is nothing but f conjugate omega. So we are conjugating both sides. We are going to get f of minus omega is nothing but f conjugate of omega. So this is only for the real valued signal. So these concepts, what we are dealing, these are only for the real valued signals. So what are the concepts that we are basically studying? These are for the real valued signals. The next point is for real and non-symmetric signals, f of t, real and non-symmetric means there is nothing like even symmetry, there is nothing like odd symmetry. F of omega is generally complex. Verifying the conjugate symmetry. I have already told you, if suppose f of t is a real signal, it is not having any symmetry, then f of omega is generally complex number. It has a real part and the imaginary part. And the real part of f of omega is even nature, and the imaginary part of the f of omega is the odd nature. And I have already told you, as the real part is even and the imaginary part is odd, then f of omega is also called as an even conjugate. And I have already proved, f of minus omega is called f conjugate of omega. So do the conjugate of both sides, then we are going to get f conjugate of minus omega is called f of omega, because conjugate cancels. We are going to get. So vice versa is also true. And I have already told you, the real part of f of omega is always even nature, and the imaginary part of the f of omega is odd nature. This point I have already told you. So therefore, if suppose f of t is the real signal which is not having any symmetry, then in that case, f of omega is generally a complex number. There is a real part and the imaginary part, and the real part is even and the imaginary part is odd. And as the real part is even and the imaginary part is odd, that is the reason it is called as the even conjugate also. And I have already told you, f of minus omega is called f conjugate of omega. With f conjugate on both sides, then we are going to get f of omega is called f conjugate of minus omega. These points already have proved, right? So this point you have to keep in your mind. The next point is, for real and even f of t, f of omega is a purely real and even. So if f of t is a real signal as well as an even signal, then f of omega is a purely real as well as even. Same thing we have already told you. Suppose if f of t is a real as well as even signal, then f of omega is a purely real, and the real part is always even in nature. So for real and even f of t signal, f of omega is a purely real as well as even. For real and odd signal of f of t, f of omega is purely imaginary and it is odd in nature. This point I have already told you so many number of times. So whenever the f of t is a real signal as well as an even signal, then f of omega is a purely real and it is also even nature. When f of t is a real signal and the odd in nature, then definitely f of omega is a purely imaginary and odd in nature. So finally, we can say when f of t is a real signal with even nature, then f of omega is also purely real with even nature. For f of t is a real signal and odd nature, then f of omega is purely imaginary and odd in nature. This point already have proved. So this point always you have to keep in your mind. So finally, if I do the analysis, how can I do the analysis in the time domain and in the frequency domain? See here, see. If you know these two things, getting these two is a piece of cake. So how to do? How you listen carefully. Time domain f of t and the frequency domain f of omega. See, in the time domain, if f of t is the real signal and real signal, then in the case of f of omega, it is also purely real and it is also even nature. Suppose if f of t is a real signal with odd nature, odd symmetry, then f of omega is a purely imaginary and it is odd nature. So now what you have to do is to replace real by imaginary. Replace real by imaginary and even by odd. Then what you are going to get? See here what I will do. Replace real by imaginary, opposite. Here also replace real by imaginary. Remaining things are same. Here also replace real by imaginary and replace imaginary by real. And the remaining things are same. So if you know first two things, just interchange these two things. So here real means what is the opposite here? Real opposite is imaginary. Here real opposite is imaginary. And here real opposite is imaginary. Here also imaginary opposite is real. But the remaining things are same. Here also even. Here also even, here also even. Here odd, here also odd. Here also odd, here also odd. The only thing is you have to replace only these things. These things only you have to replace. Here real means imaginary, real means imaginary. Real means imaginary, imaginary means real. These only things. So if you have first two things, you can get the remaining things in a very easy piece of cake. So finally I can say, if f of t is the real signal with the even nature, then f of omega is purely real and it is also even nature. Suppose if f of t is a real and also odd in nature, then f of omega is purely imaginary with odd nature. So now replace real by imaginary, replace real by imaginary, replace real by imaginary and replace imaginary by real. And the remaining things are same, even, odd. So finally I can say, in a time domain f of t is a real signal as well as even nature, then f of omega is also purely real with even nature. If f of t is a real signal with odd nature, then f of omega is purely imaginary with odd in nature. So now replace these things, replace real by imaginary, real by imaginary, real by imaginary and imaginary by real, opposite, vice versa, but remaining things are same. So if you know first two things, getting the remaining two things is a very piece of cake. So these things always you have to keep in mind. The next point that we are going to discuss, which is the Fourier transform of the periodic signals. So if you are going to apply the Fourier transform for the periodic signals, then what things will happen, which is the magnitude of the f of omega is equal to 2 pi into the Fourier coefficient magnitude of the periodic signal. So magnitude of f of omega is equal to 2 pi into the Fourier coefficient magnitude of the periodic signal. And the phase angle of f of omega is equal to the phase angle of Cn. Phase plot is same for both. So you can see clearly this important point you have to keep in your mind. So suppose if you are going to apply the Fourier transform for the periodic signals, then we can say that the magnitude of the Fourier transform is equal to 2 pi into the magnitude of the Fourier coefficient for the periodic signal. The phase angle of f of omega is equal to the phase angle of the Fourier series coefficient, which is C of n. So phase angle plot is basically same for both the Fourier transform as well as the Fourier series as well as the Fourier transform. So therefore we can say, whenever you are going to apply the Fourier transform for the periodic signal, then the magnitude of the f of omega is equal to 2 pi into the Fourier series magnitude of the periodic signal plus the Fourier series magnitude, which you can say the Fourier coefficient magnitude of the periodic signal is whatever the magnitude of the periodic signal Fourier series coefficient, and you have to multiply by 2 pi in order to get the magnitude of the Fourier transform. And the phase angle of f of omega is equal to the phase angle of Cn, means the phase angle plot is same. It is same in both the Fourier series as well as the Fourier transform. So the phase angle plot is same in both the Fourier series as well as the Fourier transform. So finally I can say, if you want to apply the Fourier transform for periodic signals, and I've already told you Fourier transform is applicable for only periodic signals, but in case if you want to apply the Fourier transform for periodic signals, then the magnitude of the f of omega is equal to 2 pi into the magnitude of the Fourier series coefficient, the magnitude of the Fourier series coefficient. Simply we can say like this, magnitude of Cn. Now you can write is equal to 2 pi into 2 pi into magnitude of Cn, we can write magnitude into 2 pi into magnitude of Cn. Simple, you can write like this, right? 2 pi into magnitude of Cn. So the magnitude of the Fourier transform is equal to 2 pi into the Fourier coefficient magnitude of the Fourier or the periodic signal, or simply 2 pi into mod of Cn. Mod of Cn is nothing but it is the magnitude Fourier, it is the magnitude of the Fourier series coefficient of the periodic signal. It is the magnitude of the Fourier series coefficient of the periodic signal. So finally, I can say that we can say the magnitude of the f of omega is equal to 2 pi into magnitude of C of n, and the phase angle of f omega is equal to phase angle of Cn. So phase angle plot is same in both the cases. So finally, I can say only one important thing, which is if you want to apply the Fourier transform for the periodic signals, then the magnitude of the f of omega is equal to 2 pi into magnitude of C of n, and the phase angle of f of omega is equal to the phase angle of C of n. So finally, whenever you want to apply the Fourier transform for the periodic signal, the magnitude of f of omega is equal to 2 pi into magnitude of C of n, and the phase angle of f of omega is equal to the phase angle of C of n. So phase angle part is same in both the cases, in the Fourier series as well as the Fourier transform. The magnitude of f of omega is called as the magnitude of the Fourier transform, and phase angle of f of omega is called phase angle of f of omega. So magnitude of Cn is nothing but it is the magnitude of the Fourier series coefficient of the periodic signal. That's it. It's a very simple thing. Just for magnitude multiply by 2 pi and phase angle same as it is. So now the next thing is, for any signal f of t, f of omega is well defined for all omega when the integration of t is equal to minus m to plus m t mod of f of t dt less than infinity. So I already told you, when the Fourier transform is going to get exist, if the signal is absolutely integrable, then only we can say the Fourier transform is going to get exist, and it is defined for each and every value of the omega. So if the signal is absolutely integrable, then we can say, or simply we can say the signal is said to be energy signal. Absolutely integrable means energy also, because square is nothing but energy. So integration of t is equal to minus m to plus t mod of f of t whole square dt. It is also energy signal. So if the signal is absolutely integrable, or if the signal is energy signal, then the Fourier transform is going to get exist, and it is defined for each and every value of the omega. So therefore we can say the given signal is a energy signal, or if the signal is absolutely integrable, which is integration of t is equal to minus m to plus t mod of f of t dt is less than equal to this, we are going to get some finite value, then the signal will have the Fourier transform, and is defined for each and every value of omega. So that is the reason which is called as a well defined. The next point is, LTI system is stable when integration of t is equal to minus m to plus t mod of h of t dt less than infinity. It means Fourier transform of h of t is must be well defined for all omega. So what is the meaning of this one? Suppose if you take an LTI system, for the LTI system the impulse response is h of t. So for delta of t the impulse response is h of t. Suppose if the h of t is absolutely integrable, then definitely we can say the system is said to be stable. Similarly, if it's absolutely integrable means the signal is an energy signal. So if it is an energy signal means definitely we can say the Fourier transform is also going to exist. So I already told you this one. So whenever the Fourier transform is going to exist means by default the signal is said to be stable, the system is said to be stable. So suppose for h of t, if the Fourier transform is going to get exist means then the default the LTI system is said to be stable. So listen carefully. Suppose h of t is there. So h of t is there, right? Suppose h of t is nothing but, suppose for a LTI system the impulse response h of t. Suppose h of t is absolutely integrable, or you can say the h of t is energy signal. Then what is going to happen? And the Fourier transform is going to get exist, right? If the signal is absolutely integrable, then we can say the system is also stable. Stable means the impulse response should be absolutely integrable. So we can say finally, if the impulse response is absolutely integrable, so if the impulse response is absolutely integrable, so what is the meaning of this one? Then we can say the given system is stable, as well as the Fourier transform for the h of t is going to exist. So this is what we can say. So if the impulse response is absolutely integrable, then the given system is said to be stable, as well as the Fourier transform is also going to exist. So therefore we can say for a given LTI system, if the impulse response is absolutely integrable, then the given system is said to be stable, as well as the Fourier transform is going to get existence. It is defined for each and every value of omega. Means the Fourier transform of h of t is defined, means it is defined for each and every value of the omega. Means it is called as again defined. So finally, I can say, suppose you take a LTI system. Further, if you given a delta of t, we got impulse response h of t. Suppose if it is absolutely integrable, then we can say the given system is said to be perfectly stable. And also, the Fourier transform for this impulse response is going to exist. And also, it is defined for each and every value of the omega. Hence, it is well defined. So now we'll discuss one more important point, which is the types of the Fourier transform. So we are going to discuss the types of the Fourier transform. So we'll discuss the different types of Fourier transform. The first thing is well-defined Fourier transform. What is the meaning of well-defined Fourier transform? For each and every value of omega, we are going to get some finite value of f of omega. Well-defined Fourier transform is for each and every value of omega, we are going to get the finite value of f of omega. Then that is called as the well-defined Fourier transform. The second point is limitedly defined Fourier transform means not defined for some omega. So limitedly defined Fourier transform means it is not defined for certain values of omega. Means if we substitute those values of omega, we are going to get infinite value of f of omega. So that is the reason it is not defined for certain values of omega. The next thing is won't exist Fourier transform for all omega. So won't exist Fourier transform for all omega. For all omega. So what is the meaning of this one? So listen carefully. Well-defined Fourier transform is whatever the given signal should be energy signal. Suppose if f of t is an energy signal, then we can say that given signal has a well-defined Fourier transform. Means it is defined for each and every value of omega. We are going to get the finite value of f of omega. Limitedly defined Fourier transform means not defined for some omega. What is the meaning of this one? See, the given signal is not an energy signal. But still, the Fourier transform is going to exist only for a few values of omega, but not for all values of omega. So this is what we have to keep in mind. See, if f of t is called energy signal, then the Fourier transform is well defined. It is defined for each and every value of the omega. Suppose if the given signal is not an energy signal, but still the Fourier transform is going to exist only for few values of omega, but not for all values of omega. Means for the remaining values of omega, the f of omega tends to infinity. So this is a point we have to keep in mind. That is the reason this is called as the limitedly defined Fourier transform. The next one is won't exist Fourier transform for all omega. So this is another case which is won't exist a Fourier transform for all type of omega. So in our course we have learned about the well-defined Fourier transform as well as the limitedly defined Fourier transform. These two things we have discussed in a very detailed manner, right? So in our course we have learned about the well-defined Fourier transform as well as the limitedly defined Fourier transform. We have learned in a very detailed manner. So finally, I can say the types of Fourier transform means suppose if the given signal is an energy signal means the signal is absolutely integrable, then we can say that the Fourier transform is going to exist for that signal, and it is also well defined. Means for each and every value of omega, we are going to get the finite value of f of omega. Suppose if the given signal is not an energy signal means it is not a well-defined signal. It is not an energy signal. Means it is not absolutely integrable. Then what is going to happen? Then simply we can say that even though Fourier transform is going to exist, it is defined for only certain values of omega, but not for other values of omega. Because if you substitute other values of omega, it is going to tend to infinity. So that is the reason this is called the limitedly defined Fourier transform. And the third one is the won't exist Fourier transform for all omega. There are some signals. For those signals, the Fourier transform won't exist for all values of omega. So only there are three types of Fourier transform. One is a well-defined Fourier transform, limitedly defined Fourier transform, and there is nothing like won't exist Fourier transform for all omega. Now the next thing is energy signals will have the well-defined Fourier transform. I already told you energy signals will have the well-defined Fourier transform. So all the energy signals are nothing but they are absolutely integrable signals. So definitely they have well-defined Fourier transform. Power signals will have limitedly defined Fourier transform. So this is not an energy signal, it is a power signal. So this is a power signal. So this is not absolutely indurable. This is not absolutely indurable. But still, the Fourier transform is going to exist only for certain values of omega. That is called as the limitedly defined Fourier transform. So power signals will have the limitedly defined Fourier transform. It's only for certain values of omega it is defined. And for remaining values of omega it is undefined. Undefined means it tends to infinity. Neither energy nor power signals will not have Fourier transform. So this table you have to keep in your mind. So listen carefully. This you have to keep in your mind. So types of signals. So types of signals and the Fourier transform. So Fourier transform. So listen carefully. Suppose if it is an energy signal, then we have well-defined Fourier transform. Then we have well-defined Fourier transform. Suppose if the given signal is a power signal, then we have limitedly defined Fourier transform. We have limitedly defined Fourier transform. If the given signal is not an energy signal, it is not a power signal, then the Fourier transform won't exist. It won't exist. So at this point, this table you have to keep in your mind. So if you remember this table, just by signal, we can tell whether the Fourier transform exists or not. Just by knowing this signal pattern, we can say what is the thing. So I want you to remember this table. So therefore, we can see clearly, if a given signal is an energy signal, then the Fourier transform is a well-defined Fourier transform. If the given signal is a power signal, then the Fourier transform is a limitedly defined Fourier transform. And if a given signal is neither energy signal nor power signal, then the Fourier transform won't exist. So this point always you have to keep in your mind. So finally, I can say, if a given signal is an energy signal, then the Fourier transform is a well-defined Fourier transform. Is for each and every value of omega, we are going to get a finite value of f of omega. If a given signal is a power signal, then we can say that the Fourier transform is a limitedly defined Fourier transform. Is for only certain values of omega, we are going to get the defined f of omega, or not for other values of omega. Means for other values of omega, f of omega tends to infinity. If a given signal is neither an energy signal nor neither a power signal, the Fourier transform won't exist. This table always you have to keep in your mind. So therefore, we can say that if a given signal is an energy signal, then we have a well-defined Fourier transform. If a given signal is a power signal, then we have limitedly defined Fourier transform. If a given signal is neither an energy signal or neither a power signal, then the Fourier transform won't exist. This point you have to keep in your mind. So now the next thing is, generally Fourier transform defined for periodic signals because they satisfy the condition which is integration of t is equal to minus f to plus t mod of f of t dt less than infinity. I have already told you, if a given signal is absolutely integrable, if a given signal is absolutely integral means we can say it is also energy signal, then the Fourier transform is a well-defined Fourier transform. It is a well-defined Fourier transform. So this point always you have to keep in mind. So therefore, I have already told you, if a given signal is absolutely integrable, is integration of t is equal to minus f to plus t mod of f of t dt is less than infinity. If mod of f of t dt is less than infinity, mod of f of t whole square dt is also less than infinity. See, suppose 2 is less than infinity, 2 square is also less than infinity. So definitely we can say, if this is less than infinity, this is also less than infinity. So if a signal is absolutely integrable, or we can say if a given signal is energy signal, then we can say that simply we can say the Fourier transform is a well-defined Fourier transform. It is defined for each and every value of omega, and the Fourier transform is applicable for the aperiodic signals. So these points always you have to keep in mind. So finally we can remember, if a given signal is an energy signal, then the default the Fourier transform is going to get defined, which is a well-defined Fourier transform. If a given signal is a power signal, then the Fourier transform is a limitedly defined Fourier transform. If a given signal is neither an energy signal nor a power signal, then the Fourier transform won't even exist. Energy signal means I have already told you, energy is equal to finite and power is equal to 0. Power signal means energy is equal to infinity and power is equal to finite. Here neither energy signal neither power signal means energy is equal to infinity, power is also equal to infinity. In that case we can say this is called as a neither energy signal nor a power signal. For these type of signals, the Fourier series Fourier transform won't even exist. So this point always you have to keep in mind. So now the next point is, Here, we can figure out the Fourier transform for periodic signals by finding them by that indirect method, but not by direct method. So we can figure out the Fourier transform for the periodic signals by finding them by indirect method, but not by the direct method. See, I already told you. We can even figure out the Fourier transform for the periodic signals by following the indirect method, but not by direct method. Means we can figure out so basically we can figure out the Fourier transform for the periodic signals by indirect method, but not by the direct method. I've already told you how to figure out the Fourier transform for periodic signal, which is mod of f of omega is equal to 2 pi into mod of Cn, and phase angle of f of omega is equal to phase angle of Cn. So first try to find the Fourier series coefficient Cn. Means it's a complex number, so try to find the magnitude, try to find the phase angle, and now substituting this formula, then we can get the magnitude of the Fourier transform and the phase angle of the Fourier transform. So this is the indirect method, not a direct method. This is indirectly. Means first we are finding the Fourier series coefficient, we are substituting this formula, and then we are going to get the magnitude of the Fourier transform and the phase angle of the Fourier transform. So we can figure out the Fourier transform for the periodic signals by indirect method, but not by the direct method. So magnitude of f of omega is equal to 2 pi into magnitude of Cn. The phase angle of f of omega is equal to phase angle of Cn. So therefore we can say that Cn is the Fourier series coefficient of the periodic signal. So first try to find the Fourier series coefficient Cn. Cn is a complex number, it has a magnitude and the phase angle. So try to find the magnitude and multiply by 2 and 2 pi in order to get the magnitude of the f of omega, and try to find the phase angle and equal to the phase angle of f of omega, then we are going to get this one. That's it. So this is indirect method. Means directly f of omega we are not defining any signal f of t. We are finding the signal, substituting this formula. So this is called as the indirect method. Directly you are applying the f of omega on a signal f of t. Like that we are not doing. We are indirectly we are taking the signal values and we are using them in order to get the Fourier transform for the periodic signal. Directly means applying the Fourier transform on the direct signal f of t, but we are not applying like that. So with the help of Cn, we are finding this one. So that is the reason it is called as the indirect method. If you are directly applying the f of omega on the f of t, then it is a direct method. If you are taking the help of C of n in order to figure out the Fourier transform, it is a indirect method. So we can say we can figure out the Fourier transform for the periodic signals by indirect method, but not by the direct method. So suppose this is a rectangular pulse. This is a rectangular pulse, the time domain, and f of t with respect to t. This is a t by 2, this is minus t by 2. And here, its peak value is 1. Its peak value is 1. So what is the area of the signal? The area of the signal is equal to, here, this is 1 and this is t. So limit the breadth, t into 1 is equal to t into 1. T into 1 is nothing but t. And what is the width here? Width of the signal? T. So if you want to apply the Fourier transform, what is the formula? The Fourier transform of f of omega is equal to, simply we can say, basically the signal is absolutely integrable. This is absolutely integrable, or we can express energy signal. So therefore, the Fourier transform is a well-defined Fourier transform. So f of omega is equal to, what is the area? Area is nothing but t into psi of omega into width by t. So this formula you have to remember. What is f of omega? Area into psi of omega into width by 2. So this is a formula you have to remember. F of omega is equal to area into psi of omega into width by 2. The area is nothing but t and width is equal to t. The substitute here. So t into psi of omega t by 2. So this is what that we are going to get. So for the rectangular pulse, here first try to find the width and try to find the area. And the Fourier transform f of omega is equal to area into psi of omega into width by 2. So this formula you have to keep in your mind. So area we know, width we know. This substitute, we are going to get the Fourier transform for this rectangular pulse. So what is psi of t? Psi of t I have already told, sin t by t. It can be anything. Here, in case of t, anything, any dummy variable can be there. So psi of a dummy variable, same thing, sin of a dummy variable by the dummy variable. This psi is called the sampling function. Psi is called as a sampling function. As I have already told you, psi of t is nothing but sin t by t. Sin t by t. Psi of any dummy variable is equal to sin of the dummy variable by the dummy variable. So remember, psi of t is equal to sin t by t. Psi of any dummy variable is equal to sin of the dummy variable by the dummy variable. Sa square of the done variable is nothing but first write these values, I can do the square of that one, whole square. Sa square of the done variable is equal to sin of the done variable by the done variable whole square. So this one always you have to keep in mind. So always remember, which is sa of x is equal to sin x by x. Sa square of x is nothing but just sin x by x whole square. Very simple, right? This is called as the sampling function. So now the next thing is we are going to apply the time shifting property. So in the Fourier transform properties that we are going to learn, So for f of t, if the Fourier transform is f of omega is nothing but it has a magnitude average phase angle. So magnitude of f of omega into e to the power of j of phase angle of f of omega. So if you are doing a time shifting, then what is going to happen? Suppose if you are going to provide the time shifting, then what is going to happen, which is f of t plus t naught means the Fourier transform is f of omega into e to the power of j omega t naught. F of t minus t naught is nothing but the Fourier transform is f of omega into e to the power of minus j omega t naught. This point you have to keep in mind. So this is what that we are going to get. Suppose if you want to write in the polar format, then the magnitude of f of omega is the magnitude of f of omega to the power of j of phase angle of f of omega plus j omega plus j common have taken plus omega t naught. Here to the power of j of here phase angle of f of omega minus omega t naught because j have taken outside. So this is a point we have to keep in mind. And I've already told you one important point. Right? In the Laplace transform, I've already told that suppose f of t has a Laplace transform f of s, then f of t minus a has a Laplace transform e to the power of minus as into f of s. Suppose here a is equal to t naught, then what is going to happen? T minus t naught is nothing but e to the power of minus s t naught into f of s. Suppose if you want the Fourier transform, just replace s by j omega, then what you are going to get? Replace s by j omega, you are going to get minus j omega t naught f of omega. Replace s by j omega. So you can write like this. This is what you are going to get. This is what you are going to get. Here minus means here minus, here plus means here plus. Same thing I have discussed, right? So same thing, here plus means here plus, here minus means here minus. Same thing. So f of t plus or minus t naught will have the Fourier transform f of omega into e to the power of plus or minus j omega t naught, plus or minus j omega t naught. Here plus means here plus, here minus means here minus. This thing is very simple. Find the magnitude and the phase angle. Here magnitude of f of omega into e to the power of j of phase angle of f of omega plus omega t naught. Here magnitude of f of omega into e to the power of j of phase angle of f of omega minus omega t naught. This is a very simple thing. And now, for delta of t, the Fourier transform is 1. For delta of t plus t naught, by using this property, what we can say? Delta of t plus t naught is nothing but f of omega is 1. So 1 into e to the power of j omega t naught, which is nothing but e to the power of j omega t naught. Delta of t minus t naught is nothing but use this formula. So 1 into e to the power of minus j omega t naught. So that's it. So delta of t has a Fourier transform 1. So delta of t plus t naught has a Fourier transform e to the power of j omega t naught. And delta of t minus t naught has a Fourier transform e to the power of minus j omega t naught with the help of this formula. Suppose if I add these two things, means here also you need to add this. If the LSR added means add the RHS also. So delta of t plus t naught plus delta of t minus t naught. So what is the Fourier transform? Add these two things. If you add these two things, you know e to the power of d theta is nothing but cos theta plus j sin theta. So if you add these two things, we are going to get 2 cos theta means 2 cos of omega t naught we are going to get. Similarly, suppose if you subtract these two things, then you also need to subtract. And if subtract these two things, what we are going to get? Simply, we are going to get is 2j sin omega t naught you are going to get. So from this what I can say? So from this what you have learned? Similarly, suppose if you add these two signals, then what you are going to get? Suppose if you add these two things, then f of omega is common. Then if you add, so f of omega is common, and these two things to take common and add these two things, we are going to get 2 cos omega t naught into f of omega. So 2 f of omega into cos of omega t naught. Suppose if you subtract these two signals, so f of omega is a common, then we are going to get f of omega into 2j sin omega t naught. So 2j sin omega t naught into f of omega. This is a very basic concept. So if you know this basic formula, you can get these things. and also you can get these things. Just you have to remember the formula. Just you have to remember the formula. Then everything is a very piece of cake. Then everything is a very piece of cake. So this is what you have to keep in your mind. So always you have to remember the formulas. Then only we can make things happen very simple.